Yeah, and then we should start. Now it should start.
Okay, thanks. Then we can go live in just a second. Waiting for the connection on the YouTube channel.
Okay, I'll be here for the first 10, 20 minutes and I'll just follow on
All
Slack.
right.
If there are any problems, message me.
Okay. All right. Good morning, everyone. I hope you can hear me fine. This is the PLDI quantum tutorial that you're dialed into. Let me put up the title slide, Programming Quantum Computers, a Primer. It's a 2/3 of a day tutorial that we have designed. And before I get started, I want to say a few procedural things. Let me just quickly stop the screen sharing while I'm talking over here. Well, that's the first problem. It doesn't like for me to stop that. Hang on a second. Okay. So we have two different channels that we're actually broadcasting. One is a Zoom channel, one is a YouTube channel. All of these channels are set up as a webinar where you can basically only listen, but you should have received a URL for the Slack channel. There's a corresponding Slack channel, and on that Slack channel, you can then actually monitor questions that are asked or post your own questions. Now, there's a caveat over here, and the problem is the following. The Zoom channel is ahead of the YouTube channel by about 20 seconds. There's a delay in that. So we may sometimes get questions, and the questions seem like they were 2 slides ago or so, but they're coming in late. So stay with me. And the way I work this is I actually have an assistant, one of my students, who stands by and monitors both the YouTube channel and also the chat on Zoom. So Zoom is for those who cannot receive YouTube in their countries due to whatever restrictions the countries have imposed. You could, in principle, use chat on Zoom directly, but it would probably be easier if you use the YouTube, the Slack channel for comments and questions as well. So the Slack channel is the hash quantum tutorial under the PLDI, and maybe Anka, Anka's my assistant over here, if you can chat that URL to all the Zoom participants, that would be quite helpful. All right.
Okay, I'll do that.
Thank you. Anka will also be the one who, when he sees questions that are pertaining to the material and he thinks they should be asked, then he will alert me, and at that point in time, come in with his microphone and read out the question to me so I can respond to that. All right, with that said, let me actually go back to the presentation and come to first slide mode over here. Yes. Well, the idea that we had for this tutorial is the following. We really wanted to bring quantum computing to computer science, ECE students and faculty, those who have never heard about it. So it's an introductory course, but with the objective of actually looking at some material that is also programming related. So this is something that Greg Bird, Patrick Dreyer, and myself have prepared over the past 2 years and actually held at a number of conferences. And it's evolving. Each time, we add some material to it, we take out some other material. The area is a very active and dynamic area. There's a lot of changes in quantum computing, of course. And just to give you an overview of what we want to do, I have some introductory slides in the beginning. just to give you an idea about what quantum computing is about and where it came from. And then I'm going to bring closer to you some concepts from linear algebra as well as postulates of quantum mechanics. Those are the necessary foundations to understand what comes later. Wait a second, this is not the... Yes. Then we have a 15-minute break. This is actually correct. And talk about quantum gates, circuits, and algorithms. So this is the first session where we will actually look at a concrete quantum computer, the IBM Q machines. There are multiple devices. Most of the exercises that we walk through will not be performed on the device itself, but in a simulator. However, every program that we'll look at and you can write yourself or test yourself can as well be run on a quantum device. And I'll talk about this later. Maybe I will run on a device myself, and you can try to do the same as we go through some exercises. After another 15-minute break for lunch, or whichever time zone you are in and whichever meal you want to consume in the short 15-minute break, we will talk about another area, the quantum annealing area, which is quite different. And for that one, we are specifically looking at programming with the model that D-Wave has made available. Again, D-Wave provides a simulation mode, but we can certainly run in on the real hardware as well. Now, if all of us run at the same time, we'll see how that works, but we'll see. Another 15-minute break is planned in the original tutorial, followed by programming exercises. And I want to make a comment about this one. The programming exercises are originally designed for a smaller number of participants. So we usually get something in the order of 30 plus minus 20 participants or so, and then have multiple faculty and maybe some helpers around to actually allow people to choose from different problems and try to solve one on their own, with us basically being on the side and being able to make suggestions, answer questions, or even walk them through some of the exercises. Now, this will be difficult at the current size that we're looking at. So it's quite possible that I will present some additional material in the afternoon instead of the programming exercises. It kind of depends on A, how many people are watching at that point in time, and B, what kind of exercises are actually feasible through the online mode. And after that, we will be done. And at that point in time, hopefully you will have gotten an introduction, an idea to what quantum computing is about. And you then have the foundation to actually go off and look at a number of resources, online resources that are available. Talking about online resources, if you see the URL on the button over here, and you can certainly go to this URL if you want to. Oh, I can't go to it myself in this mode, I suppose. Let me see if I can actually go here and then click on it. Just to show you what is out there. Well, won't let me do that. There we go. It actually doesn't let me go there. That is unfortunate. All right, so there's a Google site that is actually the contains all the different material for the tutorial itself. Try see if I can do this. And at that site are programming examples as well as the slides that we will walk through. So if you take a look at that, you should see the initial homepage where it just tells you about the general structure of the talk, basically what you've seen in the slides right now. If you go to the Info tab, then the Info tab will actually show you the slides over here for the different parts and some background reading, as well as URLs. For example, later on we'll go to the Quark simulator. We'll use the IBM Q quantum experience with a number of Jupyter notebooks, and the D-Wave Leap with the Ocean software stack, again with examples. So as we go through these examples, later on, I'll say a little bit more before we have the first break. There will be some software requirements if you want to actually try this out on your own laptop at home. All right, so that said, Anka, maybe you can post the URL both on Slack and on the chat, on the Zoom chat. And that way everybody should have it. Tag it as the home page for the quantum tutorial. All right. So let's get started with today then, with the foundations. Sorry, with the introduction before we get to the foundations. And ask a simple question, what is a quantum computer? And this is really a little bit about the history of why quantum computing suddenly has become reality. One early pioneer was Richard Feynman, who said, trying to find a computer simulation of physics seems to me to be an excellent program to follow out. Nature isn't classical then. And if you want to make a simulation of nature, you'd better make it quantum mechanical. So this was in '81. And around the early '80s, a number of interesting algorithmic foundations were actually discovered by theorists, while the quantum mechanical question had more or less been solved by physics, I would say, at the time. But this is where suddenly the idea of actually building a computer came up, and the suggestion was that it should be quite feasible to do so. David Deutsch, another pioneer in the area, said 4 years later, computing machines resembling the universal quantum computer could, in principle, be built and would have many remarkable properties not reproducible by any Turing machine. Complexity theory for such machines deserves further investigation. So you can see his interest was more on the complexity side. He's a theorist, actually. But as we will later on discover, he's also one of the principal authors of papers that were extremely influential to the foundation of quantum algorithms. In fact, algorithms that have the potential to outperform any classical algorithms that you can do on a normal computer, on your everyday laptop, or even on the largest possible supercomputer that we have today. So we'll talk about the complexity theory in a moment at a very high level, I should say. Then there are Alex Kitev, Shen, and Bayali, who said about quantum computation that a simulation of quantum mechanisms is indeed an exponentially hard problem. One may think this is unfortunate, but let us take a different point of view. Quantum mechanics being hard means it's powerful. Indeed, a quantum system effectively solves a complex computational problem. It models its very self. So that's interesting in the sense that we will later on see what it means to solve a problem is a little bit different from the way you think about a computer solving an arithmetic problem. It has fundamentally different properties if you put a quantum computer to the task in the right way. And that's actually the challenge to tap into the power of quantum computing. There's certain algorithmic patterns that you need to understand. And before we get there, I'll give you a little bit of an introduction over here on what a quantum state is. When we think about classical computing and modern computing with a binary system, a classical bit can either be 0 or it can be 1. So it's head or tails in terms of a coin that you have. Whereas a quantum bit, also referred to as qubit hereafter, can be 0 or 1, or a linear combination of 0 and 1 at the same time. So in other words, we have the possibility to put the state 0 with these funny symbols to the right and left, and 1 with the funny symbols to the right and left that you see over here, into a combination where some factors, alpha and beta, have the property that their absolute squares are equal, summed up are equal to 1. So that's a linear combination of 0 and 1, maybe a little bit more 0 if alpha is larger than beta, and a smaller portion of 1s, or an equal amount, 0.5, 0.5 for each. And we call this a superposition. So what is a superposition? Is it a 0 or is it a 1? I can't answer that question. It's actually both at the same time. So the spinning coin is, of course, a very simple analogy. It's not really giving it full justice, but it makes it clear that we don't know the outcome. And the spinning coin actually later on has an analog to what we see in quantum computing as a measurement problem, because later on we'll see that even though a superposition puts a qubit into some 0-1 combination, linear combination of states, when you observe, you only observe one or the other. So this is actually one of the problems in quantum computing that we're getting at in the following. What is a measurement then? A measurement based on a superposition means that we're measuring the qubit to be in some state. And we're either measuring it to be in the 0 state with a probability of absolute alpha square, or in the 1 state with a probability of absolute beta square. So what has happened? Well, what happened is the system actually initially was in a superposition, and when we measured it, we destroyed the superposition. By observing what the state is, you actually take a superposition and bring it into a discrete 0 or discrete 1 state. So let's say what we observed was the 0 state, then all that's left of this qubit at this point is a 0 state. We measure 0, and we get a probability of alpha square as our result. So quantum computing is really about having quantum states, qubits, evolve over time in a circuit and eventually measuring them. And in the measurement, you then destroy these superpositions and come up with a classical output in some sense. But you do so in a manner that allows you to repeat your experiment. And all this is really a physics experiment sort of embedded in a machine, in a computer, that lets you efficiently run through the experiment and repeat the experiment, so that next time when I measure, maybe I will get a 1 with some beta square probability. And that could be because actually I was in a superposition, and the superposition was 0.50 and 0.51. So then if I repeatedly measure, I should actually see an equal amounts of zeros and ones come out of my sequence of experiments. All right. So when we look at this in a single bit classical observation and representation, I should say, representation, when we compare that 0, 1 set of possible states with quantum is the linear combination. If we then extend our system from a single bit or qubit system to n bits or qubits, then we get a b to the n space in the classical sense, or a linear combination of 2 to the n basis states in terms of the quantum states that we're observing. So we actually have not 1 qubit, but n qubits. In each of this qubit could be in a linear combination of 0 and 1, so that the space that we're actually looking at, as you can see, is the sum over X for all these different alpha X's times the qubit itself, and the qubit being in a linear combination like up here. An operation in a classical sense, let's just say, is a Boolean operation. Anything that's non-Boolean would be created on top of it by extending it to more complex types. Whereas in a quantum, you have so-called unitary operations. These are operations that you can reverse. So think of an operation as a function that operates on some qubit x, and the result is the output of f of x. And if you have f of x, you have enough information on the quantum side to go back to the input, namely x. And that's due to the property of the operations. The operations are unitary operations that by themselves are reversible. So there's enough information left that I can actually go backwards one step and see what the input was to an operation that I applied. That's not the case in classical. You basically don't have any way in general to go back. For certain functions you may, and for others you may not. In quantum, only reversible functions are legal function. Anything that's not reversible is not a legal transformation. A measurement on a classical computer, you can think of it as a print statement, something that produces an output, doesn't really have an effect on the state. The state remains intact. We can actually use that state to continue our computation if we want. Whereas in a quantum computer, when you perform a measurement, then any superposition that you had, so this linear combination of these 0, 1 states, will collapse to a basis state, either the 0 state or the 1 state. But the combination is lost at this point in time. All we see is the probability amplitudes for the alpha square or the beta square at this point. Now that has an interesting side effect. It means that while in classical computing, I can peep at internal state at any time during the execution of a program, and I can use this, for example, for breakpoint debugging to see what my state of variables is throughout an algorithm. I can't do the same in quantum computing. If I have a program in a quantum computer and I run only part of the program up to a breakpoint, at the breakpoint, I then want to look at the state of the different qubits. Any measurement that I perform on the qubit, any qubit, will make that qubit collapse. And that means if I then resume execution, I no longer have the original linear combination of states that I had prior to the breakpoint. I only have one or the other state as a result. So that's one of the challenges in quantum computing, just to give you a background of where this comes from. But the interesting part is, while in classical computing, we have n different bits over here. And so that gives us n different states. We actually have 2 to the n states represented by complex numbers in a quantum state. And that is where the computation of quantum computing also comes in. So we can actually deal with an exponential number of states by just having a linear number of qubits. Okay, I see there's a question online. Does operations in a quantum computer being reversible imply that a quantum computer cannot be used to compute non-invertible functions, say hash functions? That is a good question. So you cannot directly use a hash function the way you would in a classical sense. Let me go back to the previous slide, because it still really pertains to that one. If you used a normal hash function in terms of what a hash function is in a classical state, in a classical computer based on some value, and then it projects some input value, and then it projects into a hash space, there isn't enough information to actually invert that hash function. However, if you encode additional information to the hash function, so you have the same hash that you say key, and it produces a value. What you can do is you can actually encode additional information in that function that typically allows you to then create a different hash function, essentially, h prime, that becomes reversible. And it's actually been shown that for any function h, or any function f in general, you can modify these functions such that they become reversible. The process of doing so is not always trivial, but it can in principle be done. Okay, so let me go to what a physical qubit is. There are different types of qubits depending on which material you're actually using, and thereby you can already see that there are different quantum devices today using diverse technologies. So you can use an individual atom or ion using electron energy levels, and you could use an electron and basically take advantage of the spin, or you could use a photon and exploit the polarization characteristics, or superconducting circuits that have charge, flux, and phase. The point over here is to actually find some way to have particles that have properties, and that properties suitable for the quantum mechanical behavior that we're looking for. So for example, the devices that you see today are ion traps that can operate at room temperature for certain elements. You have the ability to actually use lasers to put them into an excited state and transform states from excited back to ground state. Or the other one is superconducting circuits. And for those using, again, in this case, it's microwave frequencies, you can energize the using charge, flux, and phase the system such that qubits actually change into excited states or decay back into ground state. But the superconducting circuits actually have to operate at, well, ideally absolute zero. So it's in the area of millikelvins, tens of millikelvins that they operate at. And the first introductory slide up front was actually a picture of an IBM Q machine, the internals, which is using the superconducting circuit technology. We'll talk about it a little bit later. That technology is, of course, using cooling facilities based on a Josephson junction with a transmon that's basically absolute zero. Whereas the ion trap is a technology that IonQ, for example, is in the process of commercializing and operates at, as I mentioned, room temperature using lasers. So that much maybe as a background. We'll not get too much into the hardware side, maybe talk a little bit about the transmons if we have time for it. All right. So when we look at the requirements for a quantum computer, what do we actually want? We want a scalable physical system with very characterized qubits. That means, well, we want qubits that actually behave properly in terms of the 0-1 states, their linear combination, their transformations. We need the ability to initialize the qubits, typically to an all-zero state in the beginning when you start a computation. Then you evolve the computation. When the computation is done, you want to somehow bring the qubits back into that all-zero state so that another computation can actually start. You need the ability to implement a universal set of quantum gates. So think about the universal set as being the operations that are required for a Turing machine equivalent, except that you have a quantum machine equivalent over here so that you can do any operations that you desire to do. And the set of basic quantum gates can be a very small set. So typically it's something like 3 gates or so. You want a long decoherence time, longer than the gate operation time. I haven't talked about that yet. When you design a quantum circuit, a circuit is just like a VLSI circuit, a sequence of gates by which you manipulate qubits. The more gates you line up, the longer your circuit becomes. Each gate in your circuit will require some time to fire. And the more circuits you line up, the longer it takes for your entire circuit to execute. Now, unfortunately, your ideal quantum machine that David Vincenzo actually is suggesting over here doesn't exist. You have an imperfect quantum machine today. We'll get into more details about that, where over time, your states actually decay. So if you put something into a 1 state, so something like this here, then a 1 state is the excited state, and eventually, over time, it decays into a 0 state. And that's actually called decoherence. So the decoherence time of systems depends on their technology. It's a little bit longer for ion traps than it is for superconducting quantum circuits. But for the superconducting transmons, also the gate operation time is somewhat shorter. So overall, you need to limit the amount of gates that you have in order to stay within the decoherence time, or you don't really measure anything useful because everything has decayed and become zero. And of course, you need the ability to measure qubits. All right, so with these 5 things, we can then really build a quantum computer. What can we do with a quantum computer? Well, let's look at complexity theory for a moment. And everybody should be familiar with the P-NP space, so the set of classical algorithms that we know of in the polynomial space, which are easy to solve with a classical computer, versus the set of problems in the NP state that have solutions, but they are non-polynomial. So they are, for example, exponential. Then you have NP-complete ones, which are actually harder problems than the, well, how should I say it? The hardest problems within the non-polynomial problems. And again, there's some examples over here. For example, when you have a set of integers you want to determine, is there a subset whose sum is 0? That would be an example of that one. And then the NP hard problems, for which we only know exponential algorithms right now. And those are problems that are at least as hard as those in NP, potentially harder. And since we don't know the relation between P and NP, it's assumed that the two are actually different in a sense that gives us a computational limit on the complexity that you can efficiently perform algorithms on classical computers. And the interesting question is now, how does quantum computing change that landscape? So there's an equivalent set of problems on the quantum side, and I really want to just gloss at what's going on over here, where you reason about a BQP. So it's a quantum polynomial space at the bottom. Then QMA space that's equivalent to the NP space in classical, QMA complete, and a QMA hard state. The idea is that these are problems that are equivalent, but on to the classical in terms of the hierarchy, but are being solved on a quantum Turing machine. And there's actually a more complex definition of what a quantum Turing machine is. And then you have polynomial ones on a quantum Turing machine, non-polynomial ones, and so on, the complete and the hard ones. And when you look at the relation between these different sets, we actually don't know a whole lot. There's a lot of theory that could still make progress in terms of the question, how does P relate to BQP? So you can actually show that P is a subset of BQP, but we don't know if it's equal or not equal to BQP. If it was equal, then basically quantum computers wouldn't give you any substantial meaning superpolynomial benefit over classical computing. They could still give you a speed up in terms of a factor, but they are not going to give you the ability to break out of one complexity class and go to a different one. What's the relation between BQP and NP complete? Again, it's been conjectured that BQP is a proper subset of NP complete, and if that's indeed the case, then quantum cannot solve NP complete problems in polynomial time. So again, that's a conjecture. We don't know for sure. And that brings us to the question, what should we expect from quantum computers today? So complexity theory and the mathematical details aside, the hope was for quantum computing to provide supremacy or superiority over classical computing. This means that you can actually break complexity classes. So for a problem that in classical computing is known to be NP-complete, we would be able to use a quantum computer and solve that problem in polynomial time. That is what it means to break a complexity class. And that also means that we would then be able to perform calculations that would not be feasible in classical computing in the given amount of time in the same complexity class. And we'll have examples later on of that. You've probably heard of Shor's algorithm. So that's one algorithm that in theory gives you that quantum supremacy. Recently, the term quantum advantage has been used by quantum researchers to describe a situation where a quantum algorithm can significantly outperform an equivalent best-known algorithm on a classical computer. So in other words, you get a speed-up factor that is significant enough for a quantum problem to be solved, to be practical. So in other words, you may still be in the same complexity class, but it takes, say, a constant factor of 1,000 longer to solve this problem in classical computing, in which case it may actually be quite useful to have a quantum computer and solve this problem. Also associated with this is the question of how much cost do you actually have to invest in it. And with cost, we could measure cost in terms of time. That's one thing. That's what the complexity theory is actually looking at. But it could also be energy, because the question is, when we look at, for example, classical computing in terms of parallelism, you don't use a single core to solve a complex problem. You use many cores, or maybe even a supercomputer with many nodes of many cores. But that takes quite some amount of power. So could at some point, could it be cheaper in terms of energy to solve certain problems with a quantum computer? Now, bear in mind, if you have a superconducting transmon and you need to cool that down to absolute zero, that's energy that would have to be factored into the equation. But for an ion trap, not so much. And the other thing is, quantum computers are not really expected to be a replacement for classical computing, but rather you should think of them as working in tandem with classical computing, very much like GPUs, in a sense that you have a kernel, and for a very specialized kernel or algorithm that you're using inside your large computation, you have a known quantum solution which you can apply efficiently and then glean some insight for that particular kernel and use the results in the context of a classical computation that surrounds the quantum computation. So that's the image that we're after over here. And as I mentioned, there are two algorithms that are probably the most prominent ones, or the ones that have been publicized the most. Rover's search algorithm, which actually searches for n items that are unordered and can do so in O of square root n time. So that's a advantage, because it's actually an improvement over the classical search time, which would be linear. But it's not a supremacy because it doesn't break complexity classes. And Shor's algorithm, which is a factoring algorithm, the idea being that you have an n-bit integer, you're trying to dissect it into primes, whereas in classical, it's an exponential problem, but in quantum, it's a cubical problem that you can solve. If you're interested in more quantum algorithms, there's something called the algorithm zoo for it's like 61 algorithms, I think, by now for quantum problems. And those are the building blocks of quantum computing. So you can see by only having 61, it's actually a small set of known algorithms, and it's only growing very slowly. Definitely open to contributions. So it's an active research area on that as well. Okay, there's a question that I see on the Slack channel. Somebody has asked, so are there modern programming languages that are quantum Turing complete? So in principle, yes, there are programming languages for quantum computing, and you get quantum Turing completeness in a sense that you can have arbitrary algorithms that can be expressed with the building blocks that the language provides. In fact, all quantum languages that have been proposed are universal in that sense, because they all map down to a universal set of gates, mind you, different gates, and that's more of a quantum device issue. However, they are doing so for an imperfect quantum computer. We'll get to that in a moment. And that quantum computer doesn't have the Turing completeness, the quantum Turing completeness that you want for practical reasons. And I'll have to defer the full answer to that question until we see a little bit more about noise in quantum computers, and we may be able to talk about how to mitigate noise actually in software. That's the interesting part, not in hardware. At which point you would actually get to a quantum Turing completeness. But also in a fault-tolerant quantum computer, and that's the key. A little bit of this is actually in the following set of slides. There are different types of quantum computers, so we will distinguish 3 different ones. First of all, a quantum annealer, and that one is a device that's for optimization and random sampling problems. It exploits the tunneling effect, quantum tunneling, to drive a system into minimal energy energy minimum, essentially, and allows you to look at weights of qubits and interactions between qubits to then show you what the set of qubit states is that is a minimal or close to minimal state. The problem is that quantum annealers are not universal, so they are also not quantum complete. They are only designed for very specific optimization problems. And later on, we'll see some examples of these algorithms specifically for the D-Wave technology that you can actually use in the cloud today. The second set of quantum computers is based on the so-called gate model. And that's the one I mentioned earlier on in the introductory slides, a little bit on the side. So the gate model actually implements this universal set of quantum gates or operations. And then you apply these gates in sequence to transform qubit states into another set of states on the same qubits, with many examples. So IBM, Google, Rigetti, IonQ, Xanadu, and so on. The list goes on. Essentially, there's many more commercial ones coming out, but certainly even more within research labs. The problem with this is, or well, the reality with these, I should say, is that these are what we call noisy intermediate scale quantum computers, NISQ devices. And these NISQ devices are imperfect quantum computers in the sense that the noise actually affects our nice closed quantum theoretical mechanical space with all the postulates that you will see in the following, and out comes some kind of murky, noisy measurement that you have to interpret. And typically what you do is you get some output, and then you check the output for validity using a classical computer. So that's not really a hard thing. Think of it as the Shor problem, where you're trying to come up with the primes for a large number. So it's a prime factoring, right? If the quantum computer gives me some results and makes a suggestion, oh, these should be the prime factors, I can easily check if the quantum computer was correct by multiplying these prime factors together and checking if that is actually the original large number that I started out with as an input. So oftentimes checking is easy, but the problem is that the noise can be really overwhelming, especially as you scale up the number of qubits. And today we're looking in the order of 53 qubits for like Google, IBM, and usually less for the other machines. There are some larger machines in the lab that are more in the order of, well, still less than 100 qubits. This is likely to change in the next few years, so we'll probably get into the hundreds of qubits, but it's a slow process. What we really want ultimately is a fault-tolerant quantum computer. So that's the third type of machine over here. A fault-tolerant quantum computer would automatically perform corrections to noisy qubits. So in other words, we can take the NISQ noisy technology, scale it up. We have to scale it up to something a lot larger than hundreds of qubits. We may actually need as many as 1,000 physical qubits to implement one logical qubit. And then we can use, well, for example, so-called surface codes that are algorithms essentially to apply the fundamental gates that make up our Turing complete set for quantum computers. But when we perform operation on a logical qubit, we really perform it over, say, 1,000 physical qubits together in a much more complex way that allows us to compensate for error. Think of it a little bit like classical computing, where you have checksum or more complex error checking and error correcting schemes. But it gets a little bit more complicated in the context of quantum computing over here. There is no such fault-tolerant quantum computer today, simply due to the problem that we don't have a physical number of qubits that's sufficient to even build one. So you see, this is becoming, as people describe it now, more of an engineering problem. The theory of quantum physics is well understood. The problem is to build a machine with today's technologies that we have, and then scale it up to a large enough machine where we can use all the theory that we have and put it into play at a very large scale for fault-tolerant quantum computing. All right, so it took me a little bit longer to actually get to this point, but what I want to do is, after introducing the foundations of quantum computing, without a break, I'll go straight, sorry, I did the introduction over here to quantum computing. Without a break, I want to go directly into the foundations, which is linear algebra and quantum mechanics, before we then take a break. So the agenda that you see over here is not set in stone in terms of the times that you see. We may actually take the break whenever we get to the end of a section, and then pause for a moment, give everybody a bio break, especially for me. All right. So let me actually get to the next set of slides over here. We'll now take a dive into some math as well as some quantum mechanics foundations. The whole area of quantum theory is actually driven by a mathematical model that describes the physical world in terms of atoms and subatomic properties. And many of these behaviors don't have an analog in the classical world, which is one of the challenges actually for our mind to comprehend what quantum is about. So in order to understand the later material, we first have to establish some knowledge about math and concepts that pertain to the interaction of qubits and the opportunities for quantum computation. And those are based on simple linear algebra. So bear with me over here for a little bit of a review. In about 30 minutes, I will actually switch to a quantum simulator and show you a few examples of how qubit states can be visualized and then also manipulated. But before we get there, we need the mathematical background, because that's also later on needed to understand algorithms. So what we're doing over here, we're introducing the Dirac bracket notation, starting with an n-dimensional vector space of complex numbers, actually, where you have a column vector that's denoted in this notation over here, which I actually used earlier without having introduced it. All of this is really a column vector, and that's what we call a ket. So that's a ket A, which is just describing the values of a vector alpha 1 to n. And a bra is a row vector that is using the complex conjugates of the corresponding kets, which is expressed over here by the star. So then a bra is actually the adjoin of a ket, meaning the complex conjugate transpose. And so in other words, I can put these bra and kets together and then reason about states and operations over the states in time, building up a quantum circuit. But the vector space itself is a collection of vectors, and that is closed under addition, scalar multiplication, meaning you can add the vectors together, you can multiply them by any vector or by a scalar, and what you get is still within the vector space. So here are the properties for a vector space, and I'll go over this relatively fast because it's not really anything new, it's just a review. Given two vectors A, B, and maybe a third one, C, you have the following properties. Vectors are commutative, they are associative of vector addition. You have the additive identity property over here, and then there exists an additive inverse, and that we're going to use later, such that if there's a vector A, there's a minus A, such that A plus minus A is equal to 0. You have scalar multiplication. It gives you the identity. So 1 vector times A is still A. And relative to scalars. If you have scalars R and S that you, for example, multiply with, then you have associativity of scalar multiplication, distributivity of the scalar sums, and also of the vector sums. Okay, we use these properties later on when we are trying to actually show how quantum gate operations or even entire circuits manipulate states, and how we can then glean interesting algorithmic properties out of such transformations. And that's really the key over here. So think of it as a tools set for following the sequence of manipulations within an algorithm later. A basis vector is actually a set of elements or vectors in a vector space if the vectors are linearly independent, and every vector in that vector space is a linear combination of these vectors. So in other words, with linear independence, we make sure that no vector in this set can be written as a linear combination of the other ones. And here's an example when we are looking for a standard basis, say in a 4-dimensional vector space. We could simply define a standard basis as the 0, 1, 2, and 3 cat notation representations that correspond to the vector 1, 0, 0, 0, and then the 1 shifted 1 down. So that any vector, and that's really the key, can be written as some linear combination of these cat 0, 1, 2, 3 basis states in terms of then having an abstract vector A. In addition, we need to actually introduce what an inner product is, and later on we'll see another. So the inner product is the Hilbert space over the complex numbers, where we can now combine the bracket, the BA, by simply combining the components of the vector in terms of the alpha 0 times beta 0 conjugate, and the same thing for the ones. So this gives us the inner product combination and allows us to reason about essentially some of the properties that come along with the inner product. So the inner product is conjugate symmetric in terms of the inverse. It is you have by a linearity that allows you to take the factor alpha and pull it out. You have a positive infinite that says for an AA bracket that is greater than 0, then that holds as long as A is not equal to 0. And a norm that is used later on for measurement, which is the square root of the AA bracket. So we use the norm later on also when we reason about the output that we actually observe in quantum computing. Okay, so when we relate the inner product now to basis vectors, first of all, if we have an orthonormal basis, then the inner product is either 0 or 1. Next, any vector can be expressed as a linear combination of basis vectors, meaning that by having different factors for each of these vectors and then summing them up, we get a state psi, and that's a state psi is a linear combination. Now, again, remember that the E of I is pairwise independent of an E of J over here because it's basis vectors, of course. And the coefficients are derived from inner products. So in other words, when we look at an E of I state, then we can actually write that also as the sum psi E of I as bracket E of I, and that represents our state psi in the cat notation. The other product that is of interest, and we'll use that in the following as well, is of course the outer product. So for the outer product, if we have a cat A and B, and we now combine them in the following form over here, an outer product. So it's a cat bra. Then what this really does is it takes the different factors of our column vector and then multiplies it with the corresponding row vector components over here, such that we end up with a matrix that's, of course, the in dimension row by column. And what you can think of this as being is an operator that transforms the state B to a state A. So there's some operator, it takes B and then produces A. So you really have to read this from right to left in some sense. All right, so let's get into unitaries. That's important for quantum states, of course, over here. What is a unitary matrix? It's actually a square complex matrix whose adjoint equals its inverse. So if we look at the adjoint of the matrix, if it's unitary, then U times U dagger is the same as U dagger times U. It's actually the identity. Okay. In addition to that, so unitary actually makes sure that you preserve the norm of a vector. But in addition, it's Hermitian if U equals to U dagger. We'll see later on that a number of interesting unitary matrices that are the basis of quantum gates are actually not only unitary, but often also Hermitian. This becomes interesting later on when we talk about computing and uncomputing states. All right, so with this, I'd like to switch to quantum mechanics, specifically the fundamentals of quantum computing, the set of observations, postulates that have to hold for quantum computing that we cannot violate, or if we did, we no longer have a quantum computer. We no longer are operating in quantum space. The first one is saying that associated to an isolated physical system is a Hilbert space known as the system state space. Okay, and the system is completely specified by this state vector, which is a unit vector in a state space. So what you see is we have a state space, and this gives us a state psi over here that we reason about, and a state vector, of course, with also known as a wave function that has as additional property that the absolute AI squares sum up to 1. We will later on take advantage of that in reasoning about superpositions as well, so that summing up to 1 is actually an important property. When we reason about single qubits, then we use a standard basis notation, which denotes 1, 0, the column vector, as cat 0, and 0, 1 as 1. And this really is are the distinct states that are referred to as ground state and excited state. So a little aside over here, while this is just a quantum mechanics theory and practice when we build a system, the excited state is the state that over time decays into the basis state, and this effect was called decoherence. In an ideal quantum computer, you would never decohere. So a state would be preserved for an infinite amount of time. In a fault-tolerant quantum computer, you are assumed to not have any decoherence or deal with it in some other way. And this is also sometimes referred to as quantum memories that you can build. So there's, again, some theory that you can, in software, build on top of quantum error correction codes. Now, what's more important for us is a superposition of these two states is the state itself. So the state psi, that is a linear combination of both 0 and 1, is expressed by, again, a constraint that, of course, the squares of alpha and beta, the sum of the squares, has to be equal to 1. A composite system is then built as follows. Let's say we have a system A, and it's described by a Hilbert space HA, and another one B with described by HB. Then the combination of these two states is the tensor product of the two Hilbert spaces. And it's also sometimes referred to as the Kronecker product, but I'll refer to it as a tensor product in the following. And to give you an example over here, let's say we have an A that looks like this and a B that looks like that. Then what happens is a tensor product will take the components of the A matrix, and for each component, then multiply them with the entire B matrix, or space, I should say, so that in the end, for let me see if I can actually, whoops, that's not what I wanted. Obviously, in the end, you end up with essentially this block over here, corresponding exactly to the combination of the A00 times the B. Okay, so that's the tensor product. The tensor product is subsequently used to expand our space. So think of the A space being a set of states and the B space being a set of states. The combination of these is clearly creating a much larger space. And this is actually where also the exponential capabilities of quantum computing come from, in the sense that for n qubits, you actually can at the same time reason about 2 to the n different states. All right, so the standard basis for 2 qubits, as we said, is the 0, 1 combination. So for example, if we take a 0 in A and a 0 in B, and then combine them, you can do the math, then in the end you get a column vector that looks like this. And this column vector shorthand notation for that is actually the 0, 0 state in the cat notation. Now, other states, for example, 0, 1, 1, 0, and 1, 1, are obtained by simply moving the 1 further down, but you can see that these are basis vectors that span our 2-qubit space. Now, once we've gone from 1 qubit to 2 qubits, you can imagine how this actually evolves for 3, 4, or n qubits. All that happens is the vector becomes longer and doesn't fit on my slide anymore, and the ones are shifted one by one further down. So given such a basis set, then our number of qubit states that we can represent is actually 2 to the n if we have n qubits. And as I said, this is the power of quantum computing compared to classical computing, whereas in classical computing, I only have n different states at the time. In quantum computing, due to superposition, I can reason about 2 to the n different states within one execution of a circuit, essentially. So when we have n qubits, we of course get these n components of our basis vector state that then make up some state psi, where psi is actually defined as simply the sum over the alpha j's and then the different j components. So this is a vector state, not necessarily with all basis vectors. As you can see, it can be just an arbitrary vector space. Now, there's an interesting aside over here. When you think about states, you have states that are separable in a sense that you may have some factor that describes the possibility of being in 2 different states. But these are actually separable states in the sense that I can separate the 0 plus 1 tensor 1 and factor out the 1 over square root 2. And thereby I basically say I have 1 qubit, the first qubit, which can be either in the 0 state over here or in the 1 state, 0 or 1. And I have a second qubit that I know it's always in the 1 state. So I pull that one out. That's a separable state. And that's one possibility. Basically, these 2 qubits act independently. We just, in the upper part over here, pulled them together in our notation. And whereas in the lower one, we separated the 2 qubits from each other. As opposed to an entangled space. In an entangled space, I cannot separate the 2 qubits. So in an entangled space, I may say the 2 qubits are either both 0 or both 1 with equal probability. No other states may exist, and therefore I cannot separate them. That is, if one of them is known to be in 0 state, I automatically know that the other one is 0 as well. Or if one is in the 1 state, then the other one is automatically 1. And the crazy thing about quantum systems is now that you can actually reason about entangled states that are superpositioned. So I have both the 0, 0, and the 1, 1 state represented within a quantum computation. Let me get to postulate 2. That one is stating that every observable attribute of a physical system is described by an operator that acts on the cats that describe the system. So the cats were these things over here, right? So observable here means it's something that we measure. So that depends on the material that we're using for our quantum computer. And the operator itself is defined by a Hermitian matrix. Okay, so let me introduce a little bit of a background over here. Eigenstates and eigenvalues. So when we apply an operator, the state to a state, that will actually change the state. And this is what we want to do in a circuit. We have a state, we apply a gate, it will produce a new state. We apply another gate, it will produce yet another state. So we are manipulating states over time. Some states, however, cannot be changed except for the scalar multiplier. And we call these eigenstates, and the scalar lambda over here is the eigenvalue that corresponds to the eigenstate. All right, so looking at postulate 3, when we measure an observable, then the only possible outcome is going to be an eigenvalue of the operator for that observable, which means that the measurements that we get are always some kind of real numbers. We have to interpret their meaning in terms of the state that it corresponds to. The operator over here is again described by a Hermitian matrix, and that one has real numbers as eigenvalues, and that's the reason for this. Now, when we measure eigenstates, then what happens is we basically quantize the measured quantities over here. So when we look at the eigenstates of a AJ of a Hermitian operator, they actually form a basis in that they are orthogonal, and that any state can be expressed as a linear combination of the eigenstates. Now, mind you, this is in a complex number space, so it's a little bit more complex, as the name says. We'll get into that later. The effect of the complex numbers will later on actually be seen by gate manipulation. So in some states, you don't see the effect of the complex numbers. You will have to then apply some gate manipulations to make it visible, but it's possible to do so. All right, so let's say we have certain measurement operators, and this is actually realistic. So there's a so-called Z gate that's defined by a unitary matrix over here, and then given two eigenstates 0 and 1 with eigenvalues +1 and -1, we can then actually apply a Z to the cat 0 state, which, if you do the math, will give us, as a result, still a 0. And if we apply it to a 1 state, the Z, then it will give us a -1. So what we see in this case is a positive or a negative factor for the eigenvalues. It's the +1 or the -1 that we are observing as a result of the measurement, and interpreting as cat0 or cat1. So that's actually what's happening. You have a system. The system is driven into eigenstates for each qubits, and then you perform a measurement, and the measurement means I have a z-gate, and I just fire the z-gate, and then somehow have the ability to measure and say, oh, the eigenvalues are plus or minus, and depending on that, I can already give you the eigenstate. So there's actually a translation from the measurement in classical back to the eigenstates that you don't have to deal with the eigenvalues when you actually look at a real quantum computer. All right. So let's look at postulate 4. When we have a system that's in a state psi, and we want to measure an observable, then what this means is we're actually getting the probability of an eigenvalue, lambda over here, corresponding to the eigenstate. And again, what we're really measuring is, of course, the square of that, whereas the AJ psi is a probability amplitude. So you don't get the lambda value itself. You actually get the square in the end of it, and that gives you the real value. And also takes care, of course, of the complex number space in this case. So we always get a real value out of it. So what does this mean? If we measure something, again, in our standard basis, let's say we have a mixed state that's made up of some zero, some one with an alpha beta factor, then we can get two possible outcomes out of this. So this is a superposition. It could be a zero, it could be a one. Right now, it's running in our quantum computer, and it's really 0 and 1 at the same time. So it's a superposition of the 0, 1 states. But when we measure, we actually break it down into either a 0 or a 1. We destroy the superposition, which means that what we're measuring is the +1, possibly. And that means we are actually in the 0 state. And what we are really observing then is the alpha square probability over here. Or we get a -1, which is the 1 state. And what we're observing is the beta square probability. And in particular, when we think of a system being in an equal superposition of 0 and 1, then the probability that we get after we square the 1 over square root is 50% in a 0, 50% in a 1 state. So in other words, if we were, and we'll look at this later, to put a qubit in a superposition of 0 and 1, and then we repeatedly measure, then after performing, say, 100 measurements, we should get an equal number of zeros and ones out of that experiment or that sequence of experiments. All right. So what about expected values? If we take a system and prepare it in a certain state, meaning we manipulate the qubits in some way, and then measure it repeatedly using some operator A, we get a variety of results, each with a probability of essentially the AJ square. So if we run the same experiment twice, we don't necessarily get the same result. And that I already exemplified with the superposition. You get half zeros, half ones for an equal superposition of a single qubit state when you repeatedly measure. This is simply given by the probability of being in the different states and then looking at the states psi that you are preparing. And what you require is that that one is actually equal to psi psi, where A is the operator that you've applied over here. So when we actually, and this is another postulate, measure, that means we're obtaining an eigenvalue over here. We change the state of the system to become the corresponding eigenstate for that eigenvalue. So while you were in a psi state before, and the psi state was a complex superposition maybe of multiple states, you drive that complex state into a definitive single state, and what you're measuring are the eigenvalues. So this is where the debugging problem comes from. You're destroying the psi state by measurement and end up with a single legal state that is a subset of the psi state. When you repeat this, you may get a different AJ the second time, but again, it's a single one that is a valid one within psi. And what really happens is that you're collapsing the wave function, what's described as the wave function over here when the measurement occurs, and superpositions are lost. And they are lost forever. In fact, we don't even know what happened before we measured. That's one of the problems. We can only see the outcome after measurement. We don't really know how we got there. That's kind of the crazy thing about quantum computing. But we can reason about it, of course, mathematically. Okay. This means that, well, here's our curious cat looking over the rim of the box. And unfortunately, the cat, as curious as it is, cannot see what's inside the quantum computer because we don't have access to the quantum state. Once we actually measure, we get one classical value and we are destroying the quantum state. So we can't put print statements in the middle of any algorithm that we have. We can't pause, probe, resume, breakpoint, debug. Doesn't work. We can't checkpoint, restart. None of these concepts are feasible in quantum computing. All right, so let's look at partial measurement. What happens if we actually measure one qubit within a multi-qubit system? So let's say we have two qubits. This is given by the state down here. And the qubits are in some kind of combination so that, well, expressed over here by the 4 different possible states over 2 because it's square root 2 squared. And if we then measure, for example, qubit 0 to be 1, what happens? So let's say we measure only one qubit, the qubit 0. And based on what we're observing, the probability amplitudes, we're removing all the other cases where that qubit 0 could have also have had a 0 state. So we're collapsing this down to where just 2 possible states are left from the original 4 possible states that we had. That's because we haven't measured qubit 1 yet. Qubit 1 can still be in, well, either it's a 0 or it's a 1. We don't know yet because that one hasn't been measured yet. So our remaining state psi has collapsed qubit 0, but retained qubit 1 and still follows this equation over here because it has renormalized the remaining components. So you still have the state over square root 2 over here. So let's have another example where we actually have different factors for the different states. We have a certain probability that's associated 1/4 with the 0, 0 state, 1/2 square root 2 over 0, 1, and so on. And you can do the math over here. This one is 10/16, and this is 3/16. What we now do is we set qubit 1 to 1. When we measure, we observe qubit 1 as 1, which is this state or that state. Now, I mean, both of these states are still the remaining possible states, which means we are left with this component and that component, which when we add them together gives us 13/16. And that's what you see over here as an outcome for the probability that you're actually measuring. The other two probabilities are no longer an option because you've already looked at qubit 1, and that has a value of 1. Okay, there's a question on the Slack channel. Somebody's asking if I increment the index from right to left in these examples. I think it's referring to the position of the qubits. And as you can see, qubit 1 is, of course, the left qubit. It's just like you would reason about qubits being the least significant bit is qubit 0 on the very right side. So that's index 0, and that one is index 1 over here. And that should clarify it. Think about least significant bit to most significant bit. That's how we actually refer to it. Be careful about that. Some papers actually go the other way around. If you read something, some web page online, you first have to always infer what their assumption about the index ordering is. But these slides and mostly you will consistently see this notation. All right. So what about entanglement then? The measurement that I performed on a single qubit was assuming a separable state in these previous examples. If I have an entangled space, things change. How so? Well, let's say we measure qubit 1 to be 1, which means that we're in this state over here. So what happens in this case is that we actually end up with a probability of 0.5 being in a state 1, 1. Why is that so? Well, it turns out that if we measure qubit 1 to be 1, and it's an entangled state where the state was described by this psi over here, that we have some correlation knowledge. You may want to think of it like that. If we measure qubit 1 to be 1, we actually know that qubit 0 must also be 1. Because there's only two possible states, either 1, 1 or 0, 0. So when I measure one qubit, I automatically know what the other qubit is without measuring it. That also means I'm collapsing the other qubit as well when I measure. So this is kind of a different problem now, and one that doesn't have an equivalent one in classical computing. With the entanglements, I am collapsing multiple qubits, and I collapse them to a single known state that correlates in some way. Postulate 6. When we evolve a closed system over time by gates and so on, then we perform unitary transformations. That's what it means to actually evolve the system. We take some state psi, and that's at time 1, and transform it into a psi prime at time t2, and do so by applying a unitary operator to the original state psi to then transform it into psi prime. And as you can see, there's time now coming in, which already denotes the ability to think of algorithms in gate quantum computers by actually driving gates over time to transform states. So in that, it looks a little bit like a classical circuit. From here, we can build quantum programs. And that's just evolution over time over gate manipulations from state to state to state. Each step over here must be unitary, meaning it preserves the norm so that the sum of the probabilities of the absolute square is 1. It has an inverse, so each operator that we apply has an inverse as well, so that the computation can be reversed, and the system is closed, meaning we have no interaction with the environment. This also means that our measurement collapses the internal state. The measurement is irreversible. That is, we cannot reconstruct the original state by just looking at measurement. And if you think of a unitary transform, it really is a rotation of a vector in some sense, which is represented typically in a block sphere. So we have a state psi that is a combination of 0 and 1 basis states, where the 0 state is manipulated by a phase angle phi that rotates around the x-axis. So it's bringing us into that state phi over here. And then we also have this EI rotation around the z-axis over here. That's right here. So that rotates around the z-axis. I'm not going to put more arrows in here. And describes the component of the 1 state, again with a sign relative to the phase. Now, what is interesting in this one is typically when you think about qubits, this is a single qubit representation that we use, and we ask ourselves, what is that qubit state right now? Typically, what you look at is you have a 0 state that's at the top of the block sphere and a 1 state that's on the bottom of the block sphere. meaning that if I rotate from 0 to 1, I perform an X rotation that brings me all the way down here. And I can come up with similar rotations in different directions, as you can see. It's quite straightforward. And it is sufficient to actually use 2 angles, even though we're in a 3-dimensional space, to then express any possible state that we have. What you don't see over here, but you will in the following, is the superposition states. We'll see that in a later description of the block sphere. So there are similar rotations that are defined around the different axes. An X gate is a rotation around the X axis with a phi angle of pi. And then a Z rotation, again with an angle of phi, actually results in the negation of the 1 coefficient over here, whereas the Y rotation is a combination essentially of X and Y with a complex imaginary added to it. So this is pretty abstract. How can we actually look at that and make sense of it? So let's see if I can actually click on this. Unfortunately, it doesn't work. What we want in this, oh yes, it does. Okay, excellent. You can try this at home if you have the slides in front of you, or otherwise just use the URL that you see at the top right now. If you go to alcassert.com Quirk, Q-U-I-R-K, and then click on Edit Circuit. I'll give you a moment just to make sure that you actually get to this point. And maybe, Sudhakar, can you also post that URL? So alcassert.com Quirk. All right. Post that URL on the Slack channel, please. And if you then click Edit Circuit, then you have a WYSIWYG quantum simulator that you're actually running just with a few qubits on your laptop in a simulator. And it's inside your browser. It's kind of nice. So you can drag and drop any of these symbols up here. What you see is a timeline. So the timeline actually goes, I'm going to drop the X right now, an X gate. I'm just going to drag it down here and put it on the timeline. So the timeline, as you see left of my X, has a ket state of 0. So we start out in a 0 state and perform a rotation with a phi angle of pi around the x-axis. So 180x will change our state from 0 to 1. And we can see that on the right side, because as you can see, I'm now clicking on this on field over here. On represents, in this case, on a block sphere, the state that's at the bottom of the block sphere, which, as you may recall from the previous slide, is actually the 1 state. So if I didn't have the X here, I can just move it off again, off this thing, and throw it basically away. We were originally in a 0 state and had a measurement of being in the 0 state. So the on state had a probability of 0, meaning we must be in the off state. That's the 0 state, also represented in the block sphere by being on top of the Bloch sphere. And as you can see, there's actually more details about the Bloch sphere in terms of the phi angle and XYZ components. So it's the Z component that's a 1 over here, and rotational angles. Okay, so let's try this. If we put the X on here, the X essentially negates a state. So a 0 state becomes a 1 state. And if we put a Y on an axis, then it acts as a rotation around the Y. So it's also resulting in on being measured. And as you can see, this one has the same observable state over here. We can't really see a difference in this particular case. So the internal state looks the same after measurement, or we can perform a Z over here, which doesn't seem to affect our state. So we stay in a 0 state, again, similar to the original one that we had. So I can remove this if I want to and actually compare these two over here if I want to. We will later on see that if you combine these, you get more complex states. And we will also then try to understand how we can look at the different amplitudes of complex, more composed results of different possible qubits over here. So here we have a single discrete result. We always get a 0. That's the first, a 1 for the first qubit and a 0 for the second qubit. That's indicated over here by our amplitude matrix. All right, so the Pauli matrices, so-called XYZ, give us the fundamental rotational gates and allow us to also perform manipulation on multiple qubits. So what I can do is I can, for example, describe a operation where I want to perform an X, so a NOT gate, on qubit 1, and I want to perform a Z on qubit 0. And I can actually look up what an X is. On the previous slide, it was this matrix, and what a Z is, there was that slide. And so what happens now with a tensor product, we essentially take the Z matrix over here and multiply it by 0 in this corner. Take the Z matrix and multiply it by 1 in the top right and bottom left corner. So you see these are the original Z matrices over here. That's just what the tensor product does. And then 0 again in the bottom right corner. Okay, so this is why you get such a matrix as a unitary transformation that composes X and Z with respect to 2 qubits. So what this is telling us is I can now take 2 qubits and perform a Z, an X followed by a Z, doesn't really matter in this case. And depending on what our input qubits are, I will come up with some output qubits. So how so? Let's try this for the moment. So the input state 0, 0 that you see over here, what would be the basis vector that describes this state? So the basis vector that describes this state is 1, 0, 0, 0. and would now have to be multiplied with this matrix over here, in which case we get 0 times 1, 0 times 0, 1 times 0, 0 times 0. So the first component is 0. The next one is 0 times 1, 0 times 0, 0 times 0, minus 1, 0. So it gives us a 0. The next one is a 1 times 1 plus 0 times 0, and so on. So that gives us a 1. And the final one is 0 times 0 minus 1 times 0, 0 times 0, 0 times 0. So that's the outcome. And when you look at the encoding of the outcome, the 1 is in the third position, meaning that it is which vector in the cat notation, which state, I should say, in the state cat notation. Well, it's the third state. So it's the third state where the most significant qubit is 1 and the least significant one is 0, which is precisely what we see over here, right? Okay, so you could repeat this. For example, for this input vector, you could do the math and you should come up with essentially this thing over here, which would tell you, actually it's an interesting one. So when you go through this, you would find, wait, did we do this right? Yeah. So you would find that you end up with, let's see, 0, 0, 0, 0, 0, 0, 0, 0. So these are all zeros. And for the last one, you get a -1, which is equivalent to just pulling the minus out of the vector, a cat state that's both qubits 1. But then we have the angle over here, which is -1. So we'll pull that out. The angle is actually something you cannot directly measure. At least here, you would only see 1, 1 in this case. But you could if you were to further manipulate and rotate this state. All right. Another 2-qubit transform that is of more interest is the C0. So a C0 is a conditional knot. And the condition here is if qubit 1 is 1, then flip qubit 0. So you can see that if qubit 1 was 0, nothing happens. The state stays as the same. But if qubit 1 was 1, then the qubit 0 changes by being negated. It becomes the opposite. It was a 0 before, and it now becomes a 1. It was a 1 before, it now becomes a 0. A C0 is a conditional, and as it says, it allows us to build in some logic, conditional logic, in a program, which we will use later on actually to design algorithms. It's a central building block that we again need. And when we look at the matrix, the interesting thing about the matrix is it is once on the diagonal, except for the lower right, where you have the inverse in the lower right for that submatrix. And that precisely gives us the negation, because as you might recall from back here, and negation is basically by putting the ones on the off diagonal. So it was a conditional one only for the two states of interest where the qubit 1 is 1. What I have introduced so far now gives us the ability to build circuits. Isn't that exciting? We finally get to write a program. A program is really as we have learned already in the postulates, step-by-step evolution from state to state to state. And in between, you have gates. Each gate is a unitary that transforms the state. So we may start with an initial state over here, then perform some gates. So we have H gates over here and S gates and T, and we don't know what that is yet. And we may also have conditional gates. So that's saying if this condition holds, if there's a 1 over here, then perform the U gate on some S0 and S1 qubits, and so on. And in the end, we may elect to measure some qubits, not necessarily all qubits, as you can see. So we just measured some qubits over here, and then get probability amplitudes and have to interpret them in terms of what that means for the state that we have observed. This is what it really means to write a quantum program. So if I may summarize at this point, a qubit is simply represented by a vector in the Hilbert space, complex Hilbert space. Systems are composed using these tensor products and evolve using unitary transformations over time, which essentially are rotations or conditional rotations. And a measurement then projects a state to an eigenstate of the measurement operator. So, for example, the Z operator as a measurement operator that we're using. In theory, a system should be closed in an environment. And with that, you have all the postulates of quantum mechanics that hold. In reality, we don't have a closed system because, unfortunately, our environment is not ideal. For example, we are not at absolute zero with the transmons. We get noise. Even with the ion traps that don't require cooling, we still get noise. So without going into the detail of these noise characteristics, we're at the point where I will, in a moment, take a break. But I want to take a look at some questions that came up over here. So one question that Sylvia asked over here is, don't conditionals measure? So that's a good question. When you look at a conditional, you see that a conditional is actually defined by a unitary matrix, which preserves all the properties of quantum mechanics. So we are still in a closed ideal state, preserving the entire state, even though we are transforming it. And that's the interesting part of it. A conditional will transform, for example, if I'm in the, you can see this over here, if I'm in the one state for the most significant qubit, then it will transform the other qubit, qubit 0. So what happens if we're in a superposition? Because this is really where your question comes from, I think. If you're in a superposition, that means, let's say for qubit 1, qubit 1 could be either 1 or 0. So what happens then if I apply a conditional to a superposition? We will see later that it actually manipulates also the most significant qubit. It has what's called a kickback effect. That is an effect, an algebraic effect, if you want to reason of it in terms of linear algebra, from the, so a C0 is actually denoted if I have 2 quantum bits over here. So let's say this is Q0, Q1. And I put a C naught in here, then that's what it would look like. That's how I denote that. So the control bit is the upper bit, and the bit that I am controlling is the lower bit in this case. And if I'm in a known state, so let's say this upper one is in a state 0 right at the beginning, and I could transform that, for example, to be in a 1 state. I know it's now in a 1 state. Then when I perform the conditional, and I assume initially both of these were in a 0 state in the beginning, since this is in a 1 state over here, it will negate the lower bit. So the outcome of this should be a 1 on the lower one. And I can check that. So I should see a 1 on the upper and on the lower. But if I am in a superposition, then I would have a different circuit. I would have a circuit where, still starting with 0 states, I put myself in a superposition. We haven't talked about this yet. It's a header mart, and then perform a control. And the outcome of it is now an interesting combination that I can't really tell, will this down here be a 0 or a 1? In fact, I can't even tell what happens up here. You would think that on top, in terms of classical conditional control, you retain your original value, but that's not necessarily the case either. There's some kickback that goes the other direction. So let me just quickly illustrate this in Qiskit. So if in Qiskit, for example, I put a C naught in here. So I did this. Let me illustrate again by just dragging an X down onto the lower qubit and take the solid dot and drag it right above. That's a C naught. And what we can see now is that the input to the upper is a 0. The input to the lower is a 0. Since the control is 0, no manipulation will be performed on the bit that we are controlling. Both of them stay off 0 in the end. If I changed the first qubit and prepared it to be in the 1 state, so it was initially 0, after the X, it becomes 1. By the way, I can check if that's really a 1 by putting a let's see, probability display in here, and I can actually drag that. Well, I should put one in per qubit. Sorry, I didn't want it here. I wanted it here. And we can see initially we were basically off. We perform an X that becomes an on, and now we will negate whatever was the input over here. So the input over here, of course, was also off. We're negating that and it becomes on. All right. So back to Sylvia's question. If I now put you into a superposition, what's going to happen? Well, half the time you're in a 0 state, half the time you're in a 1 state. That's actually not the proper way of thinking about it. I'm simplifying this. You're both in 0 and 1 in a quantum sense. You're in a superposition of that bit. But when it comes to the control, it's easier to think about half the time being in one state, half the time in the other, because what that means is I'm actually negating this bit, performing a naught on the lower bit half the time. So you end up in this other state. but it's more complex, as you will see later on. I can't take this away because it's something that comes out in the next set of slides, where we will see that it doesn't just transform control half the time down here, but it keeps both this superposition alive on the upper qubit and creates another superposition on the lower qubit that's actually tied to the upper qubit. And this is what we were talking about earlier when we said that qubits are entangled. You can actually entangle two qubits while they are in superposition. And now both of them are in superposition. So if I change one of them, it will also change the other potentially. It depends on the operation that I'm performing here. So I actually can't. I have to change this example a little bit further, but then you'll see what happens. All right. So the rest of this question, I think I'll have to defer to Sylvia. Thank you for asking. But that's it for now. Let's take a break until 11:30. As you can see, my time is my original time that I had. It's actually slipping a little bit. So we will take a break and then start at 11:30 according to my time over here. So that's roughly in 20 minutes. And then I will talk about quantum gate circuits and algorithms for specifically IBM Q, but in the beginning also in general. If you have any more suggestions or questions, please post them meanwhile on Slack, preferably. Thank you. All right, so it's time. It's time to continue. I'm not sure why this is frozen on my screen over here. I hope you guys can see me. All right, time to continue. I was just preparing for the next set of slides over here. And the next part will actually be looking at quantum gates, circuits, and algorithms with examples for the IBM Q quantum experience. It's actually more than a quantum experience. We will program a little bit with Qiskit. And just as a quick recap from the beginning, oh, actually, I should go back. There was still a question unanswered before I go on with these slides over here. Hang on a second. Hang on a second. Why did this not work? Okay, I think now we have it working. Sorry about that. So before I go to the next set of questions, there was, sorry, the next set of slides, there was a question. Atsuko was asking, since measurement collapses the superposition state, do computations on quantum circuits always need to be repeated many times? So the answer to that one is yes. It's very simple. You do have to repeat measurements for multiple reasons. One, we are not working with fault-tolerant quantum computers. In a fault-tolerant quantum computer, in theory, if you had a program and there was only a single valid answer in terms of the measurement outcome, then running once would be fine. Unfortunately, we don't have a closed system / fault-tolerant quantum computer, but we have these noisy systems. So the answer is yes, you will always have to run multiple times. And then what you try to do is you look at the set of answers, and if you're expecting a single answer as the output, you would hope that the one with the highest probability amplitude actually represents your answer. If you have multiple answers, then you may have to look at the set of highest ones, the ones with the highest probability. Now, that said, actually, why is the camera not working? That is funny. That said, it is not always possible to simply rely on the outcomes of these different measurements. The problem with that is the measurements that you get are the measurements coming out of a noisy system, and some of them may be skewed by noise so much that you actually get medium probabilities for incorrect results. So that's where I said in the beginning, it's always a good idea to, if you can, have a classical algorithm to check your result. So for example, see if you did Shor's algorithm with factoring, do the factors actually, when multiplied, provide you with the original long value that you were trying to factor. I hope this helps. So that said, let me go to the quantum gate circuits and algorithms. We already looked at what a block sphere is, and it really was a mathematical representation of the different vector rotations that you can have around the x and the z-axis, and then for the y, you typically take a combination of the x and the z-axis, such that the square of the amplitudes add up to 1. And the measurement then was a projection of the state to a basis vector. And as we know, it destroys the superposition, of course. We also learned that a gate is a transformation of a state for a qubit to another qubit. That was for a single gate, and we can represent that by a rotation in a block sphere. Each of these operations, rotations, are reversible and are represented also by a matrix. And the same can be done for multiple qubits, as we'll actually go into detail in the following. Now, a little aside, we use a basis set of 0 and 1 over here, but you could now certainly use other basis vectors if you wanted to. Sticking with a block sphere, if we now look at what happens with the X gate really acts as a NOT gate if we're initially in the 0 position over here, and we perform an X rotation of an angle pi that rotates this one down here, and we end up in a ket state 1, which is just the inverse of ket state 0. If at this point, of course, we measure, that's the idea. So you can see on the right side here the different values that we expect. This was the first row, basically. 0 goes to 1. After applying an X gate, a 1 would rotate back up to 0. But it's more complicated when you have a superposition. So if you have a superposition of some alpha zeros and beta 1s, then you essentially invert the amplitudes, that the beta becomes the factor for the 0 and the alpha for the 1. And so that's the effect that, for example, an X gate has on a superposition. It doesn't destroy the superposition, it transforms it. It transforms the amplitudes essentially for the superposition. Then how do we get in a superposition? There's actually a gate for that, and it's the so-called Hadamard gate, denoted by an H. I briefly demonstrated that at the end of the last sequence of slides. And what that does is it performs a pi rotation around the X and the Z axis. So basically exchanges X and Z. And we end up in this state over here that we denote as a plus state. Okay. So you can see this here. If the start was a 0 position, then the end is this plus state, which is really 1 over square root 2, 0 plus 1. If you start in the 1 state, that would have been the state here, and then perform the same rotation, you would end up back here in the 0, sorry, not 0. How do I go back? This is always, I can't erase it. I'll just do it this way, the cheap way. You end up in the minus state, so-called minus state. So on the x-axis in the negative direction, on top of the block sphere. And that's what you see over here in the second row. And if you were to start out in a superposition of 0 and 1, and then perform a Hadamard, you end up in the plus minus with the same alpha and beta applied to what you expect. The 0 became a plus, so that's where the alpha is retained, and the 1 became a minus. The Hadamard itself uses a unitary matrix of what you see down here. So it's 1 over square root 2, except for the last component has a negative spin. And then you can reason about what happens over here in terms of, for example, going through the first row over here. If a Hadamard is applied to 0, what is actually that transform that takes place, what is the basis vector that you see as a result. How can we actually measure that basis vector? Well, if we measure, we either measure the top or the bottom. So again, by repeated measures, and we measure the square of that, we will get half zeros and half ones as an outcome for that particular case. And as an additional question, you might ask yourself, if I end up in the minus state and I was to measure, what would I see? You would actually see the same. You would not see the fact that this has a negative phase angle to it. A negative phase angle would have to be made visible through some other transformation. And there are other transformations. So in particular, you have a Z transformation. As you can see, the Z transformation takes an initial state. Let's say the initial state was a plus state, and transforms it into a minus state over here. You can, so Z rotation is a rotation by 180 degrees, but you can have fractional, and I should say what you're really manipulating over here is this term. It's the angle in the exponent over here, and this is also the complex component that you have in terms of the complex vector space that it is spanning. If you don't desire to have 180-degree rotations, you can do a 90 or 45 degrees. So 90 degrees would be an S rotation. That puts you into this state right here. This state doesn't have any short notation. And if you have a T rotation, you're somewhere in between the X and Y axis on the block sphere, halfway in between. And if I perform a T followed by an S rotation, I would end up in between the Y and the minus X, somewhere in here. So that gives you an idea of some of the other rotations that you have. But when you measure things, of course, let's see what the outcome would be. So let's say you have an initial state 0, and then we are performing a Hadamard gate, which puts it into superposition, followed by another Hadamard gate. So first you have a rotation around the z-axis, and then another rotation around the z-axis. By having two rotations, it puts you back into the original position. So if you started out with a 0 state, your resulting state will be 0 with a probability of 1. You'll never see a state 1 in an ideal quantum computer. Now, mind you, if you have noise, it's not going to be 100% here and 0% there. It's going to be some other mix of probabilities, but it should still be with a high probability. You should see something close to 100% zeros. Now, if I put a T rotation, so that was a quarter rotation in here, then I end up, and you can do the math, because we square this and then we measure with 85% of 0 and 15% of 1. All right. So you would have to actually do the math to come up with this. I'm going to gloss over this, something you can try at home. If you have an S rotation between two H's, so the S rotation, let's go back. What was it doing? The S rotation puts us in this position, but we were already in a Hadamard. That's what we said. So in a superposition in a plus state, and now it's putting us into the Y position, which is a 50% of 0 and 1. If we do an S and a T, you get the same as here, just reversed. And if you get a Z rotation, that's actually a pi rotation that would flip the value from 0 from 1 to 0 and from 0 to 1. Okay. To build up algorithms in quantum computing and really do something that is more complex than in classical computing, you have to use Hadamards. You have to put bits into superposition. This becomes clear later on when we look at algorithms and reason about how to abstractly transform state that is a combination of 0 and 1. If you keep it in a discrete state, always 0 or always 1, you don't really gain anything with quantum computing. You're just doing circuits similar to VLSI circuits that are a little bit different in the way they are realized physically, but you're still doing classical computing. It is only through the Hadamards that you gain the advantage of quantum computing. If we look at what's called a state preparation, you start with initial states. And let's say these are input states for a function. So you have n qubits over here. You would want to apply a Hadamard to each of these qubits. And what this does is it puts all these qubits into superposition, creating a say psi of essentially the sum of the basis vectors, all possible basis vectors with a factor of 1 over square root 2 to the n. So you have 2 to the n different possible states over here, whose amplitudes are equally probable if you were to measure this. All right, so this is a generalization of saying in here, if I, well, where did we have this? I guess we didn't have it, but in here it's similar to what we had in here. You had a 50-50 chance with 2 qubits, and if we go forward and now have n qubits, it will be this term over here squared for each basis vector in terms of, or each, sorry, not each basis vector, each possible state in the 2 to the n states that you are actually reasoning about or computing by putting the n qubits into a Walsh-Hadamard transformed state. So let's go down to just 2 qubits and reason about what happens over here with the C0 again. We saw a little bit of that already at the end of the last slides. The C0 is really equivalent in logic in terms of the basis states to performing a controlled XOR on the second qubit. So we perform a NOT if qubit 0 is a 1. And we've seen the possible state transformations over here before. When you think about this, it looks like, in a classical sense, a simple, a simple source control to a target function, but it is not. It is only if we think about the basis states. If we indeed place a Hadamard on the control bit and then perform a C0, then the resulting circuit is referred to a Bell state or a state preparation for a Bell pair of qubits, which have an equal probability of 0, 0 and 1, 1. And again, if we measure this with 50%. Notice this is not representable by any tensor product. These are inseparable states. These two qubits are entangled at this point in time. And what's more is the notion of this is the control that decides if an XOR is essentially performed and a NOT results in the negation of the lower bit. This logic no longer applies. It applied over here with the 0-1 states. It didn't apply over here anymore because we're actually in this superposition state that has, well, a superposition state of the H that is now resulting in an entanglement. And if we see this over here, what's happening is if we have a simple C0 and we have some alpha beta component over here, then in the end, we get an entanglement that's just the 0-0 and the 1-1. But that is because we started out in an entangled, in a superposition over here before we created the entanglement. If we did not start out in an entangled, in a superposition state over here, and then used a C0, then it's actually not an entangling operation. So if they're over here, the assumption is basically somewhere on this line before there was an H gate. And down here, we're assuming that on that line, there were some other gates, but not an H gate. And due to that, what's actually happening is if we think about some arbitrary state of the two qubits, as a result of the C0, we get a combination of the four possible states that's defined by the pairwise product of the vector components of the first and the second qubit. So that's quite different. Above, entanglement. Below, no entanglement. And we can still generalize this in terms okay. And I was just looking at one of the comments. Somebody was saying that the live streaming is not working. 10 minutes were missed. All right, I'm sorry about that. I didn't have that experience. I'm not sure what happened over there, but I'll pay attention to that next time. All right. You have other control gates that you can create. It doesn't have to be just control X gate. You can also create a control Z gate, and it just looks the same way as any other control gate, except that the box in the right bottom corner, the 2x2 submatrix over here, changes to the respective operation that you have. So this is actually the Z matrix, and you put that in a control operation. This looks like the same way the X looked, except that this bottom part has been substituted. Or a control H. Remember, an H was 1 over squared root 2, except that this term had a minus in there. Or we can make it an arbitrary gate. Say this is a universal gate, and the universal gate would then be a combination of these four components over here. All right, so these universal gates are actually important in the sense that typically you see the quantum devices, the real devices, implement them. So they're more versatile in that you can typically define an angle, at least one angle or multiple angles in terms of the rotations on the Bloch sphere with them. And then if you have a Z or an X gate, these are specializations where only one angle is exercised. There are a few other gates that I'd like to introduce. There's a so-called swap gate that's actually denoted by an X and an X on the timeline for the qubits over here, which are connected. So a swap gate means that we're taking the value from here and move it down here, the value from here and move it up there. And this X gate can actually be realized by a sequence of C naughts. If you put three C naughts in sequence, that's equivalent to actually performing a swap. And there's a whole set of gate equivalences. If you look that up, you can Google that. You'll come up with many papers that have been published on discovering gate equivalences. They're important in that when you map down to the universal gates that have been implemented on a given device, when we program with high-level gates, there's actually a compilation step, it's called transpilation, that goes down to the native gates then and will implement this in native gates. So swaps are actually important on these architectures and will be realized, for example, with 3 C naughts like this. Now here's a fundamental principle for quantum computing, which may be surprising for those of you who have never seen it before. And it's a constraint that is unique to quantum computing, which makes it sometimes more difficult actually to program, one that you have to live with. There isn't any cloning transformation U, so there doesn't exist a unitary U such that given a state A and a state 0, if I apply U on it, I end up with a copy of A in another qubit that before was 0. So that actually is not possible. Why is it not possible? Well, let's assume it was possible. Then if it was possible, then basically you would have to have a gate that acts just like that. You have two A's in the end. And let's just say we have A and B. They are two orthogonal quantum states. So if they are orthogonal, then that means if I can clone one, I can clone the other. And for the moment, let's consider a state C. That's an equal superposition of A and B. Then by linearity, if I start with C0 and I assume that I can actually properly clone, then my cloning for A0, my cloning for B0 would result in AA and BB, as I am in the superposition over here. My factor over here remains the same. But if we assume that cloning is a legal transformation, I could clone also C, and I would get CC, which means a CC is nothing but, well, A plus B, and that's how we define C. A plus B, or 1 over square root 2, tensor A plus B, 1 over square root 2. And if I now actually performed the tensor product on that one and factored this out, I would end up with these 4 components and a factor of 1 over 2. And as you can see, this term over here is not equal to that term, which tells us there's a contradiction. So therefore, no such U exists. Cloning is not possible. You cannot copy a state. In classical computing, not a problem. I have a variable V. It has a value 1. I copy it into a variable Q. And then Q will also have the value 1. My old variable V will have the value 1. Not so in quantum computing. What I can do is I can actually swap V and Q, or X and Y. But I didn't create a copy of the value. I just swapped them. And there is this operation. I cannot copy or clone state, a qubit. All right. So with that said, okay. So let me actually see. There's a question over here. Yotam is asking if, let me go back to this one. If A0, and I don't know which slide this was on, is a shorthand for a tensor 0. And the answer is it depends on the context. In some contexts that, well, typically it's not the case. So typically that's not what we mean. So for example, if we look at this one, yeah, I guess it was in this context. This just means you have two qubits. You have one qubit that's in state A, some abstract state A denoted by psi, and another qubit that's in a known state 0. And what I want to do is I now want to take the state of A and copy it, copy it into the second one there, right? So that's what the cloning was all about. It's not the tensor right there. So, well, sorry, I didn't say that right. Yes, it is the tensor because you're creating a tensor state, and you see it here. But there's two ways to think about it in terms of performing the unitary for an abstract cloning operation, which doesn't exist over here. So I'm sorry. Yes, you can think of it absolutely as a tensor. Let me go back on that. And that's more complicated. You need to look at the context of that, unfortunately, in the slide. So yeah, that tensor is typically not expanded. All right. 3 qubit gates. We have an abstraction over here that is called a Toffoli gate. And a Toffoli gate is, again, one of these building blocks that allows you to perform certain operations that are actually equivalent to also classical computations, as we will see in a moment. So a Toffoli gate is basically we have two controls and then an X gate on the bottom, or a NOT gate. Hence, it's called C NOT. Sorry, it's a C controlled C NOT, or sometimes also referred to as CC NOT. And a Fredkin gate is a controlled swap gate. So we already saw what a swap is. The swap can be controlled by another qubit. So these are 3 qubit gates. You could come up with more complex ones. I could make 4, 5, 6 n qubit gates. So for example, an n Toffoli would be n-1 controls and 1 NOT and so on. So let's look at the Toffoli gate. It's actually kind of interesting. So the Toffoli gate can be conditioned. And that's not obvious when you look at it first. What is a Toffoli gate? It's really a CC NOT gate. But when I set the first and the second input to 1, then the third input will always result in an output, if I can, or in a transformed state, that's the negated prior state, while leaving the other 2 qubits alone. Okay, so that doesn't seem like very useful, but if we look further, we see that if you condition the last bit to be 0, then you end up with an output that's actually the logical AND of X and Y, if you condition it to 1, you end up with a NAND inside over here. And if you set the first one to 1 and the other ones are X and Y, you end up with an XOR. So depending on how you condition inputs of the Toffoli gate, you end up with a situation where you can build up basic logic gates. And as it turns out, these logic gates are sufficient for, when together with a conditional set you have, for full Turing equivalence. So that actually helps you construct arbitrary circuits, and in addition gives you the ability to mix quantum computation, say you have superpositions and entanglements, with classical computation. Say I need some basic Boolean logic. I can build on top of it some algebra on first, say, integer numbers, positive and negative, and even floating point if you want. So people have actually been looking into reversible logic gates that allow you to implement all the equivalents of classical computing. Now, why is that useful? Well, sometimes you have a quantum algorithm where you want to calculate a complex property that requires superposition, but you don't want to switch back to a classical one all the time because you collapse all your superpositions at that moment. And then it would take a while for you to maybe get back to a quantum state if you repeatedly switch back and forth between quantum and classical computing. And there are many algorithms that are of interest that do this. But rather, I could use some classical computing in the middle of quantum computing, for example, for Boolean logic, for counting, for simple purposes like that. So that's where the Toffoli gate actually comes in. And we can use these gates now in a quantum circuit. So the circuit notation was kind of introduced, not explicitly under the hood before. We have a line, and on that line lies a qubit, say J0, with an initial state. Then we perform one qubit gates, like the Hadamard on it, or we can perform multi-qubit gates. So for example, this is a control for some kind of a universal gate that is applied on S0 and S1. And what U4 stands for doesn't matter over here. It's just some U gate, probably a rotation by a quarter pi over here, and on both S0 and S1. So in the end, we will then decide to measure not all qubits, but a set of qubits. And this is essentially how you can build up arbitrary circuits. Now, in these circuits, you can use CC knots, Toffolis, that have multiple control bits, and let the transpiler later on worry about how that translates to the native gates on a machine. That's the nice thing about a quantum language. So we can try this right now and see what happens if, for example, we want to build up a simple half adder. A half adder can be realized as follows. If we have two inputs, A and B, that we want to add, then the result of them could have a sum or a carry, or both. And the sum is 1 if either A or B is 1, which we realize with two C naughts in sequence for the two bits that are controlled over here. So if A was 1 and B was 0, then our result S would be 1 in this case, which is essentially this. Whereas our C, since B is assumed to be 0, would be 0. And you can go through the other cases to verify, for example, maybe the last one, if both A and B are 1, what happens is 0 changes to, that's a naught, or C naught, becomes a 1, changes to, that's a C naught that will be applied because B is 1, a 0 again, so S should be 0 when it comes out. Whereas the 0 is changed to a 1 because both A and B are 1. So the control kicks in and performs a negation on the C position on the 4th bit. And that essentially gives you a half adder. So by the way, if you want to, you could now go to a Kirk simulation and put this particular, let me get rid of all the other stuff here. Well, actually, I can just clear the circuit, might be easier. Whoa, okay, that's interesting. Okay, let's see if I can pull this down. Something has happened here. This doesn't look good. All right, so if we want to build this circuit that we just saw, I need a C naught that's controlled, whoops, on the 3rd qubit, and a C naught that's controlled from 2nd to the 3rd. And on the 4th qubit, I need two, no, that didn't come in, two controls above that I can drag down. And you can do that yourself. And now you can actually, if you want to, look at the different, well, actually, I'm not going to do this, different possible inputs and play around with them. So for example, if I put a 1 on the B input, which was the 2nd line, then the output is a 1 on the sum, which was the 3rd line. And if both of the inputs are 1, then I want the sum to be 0 and the carry to be 1. So you can play around with all these different possible combinations and actually verify that it gives you the correct result. But all you've done is you've created a circuit that you could have just created in classical computing. So while it's exciting to actually understand the logic by which quantum gates work, you haven't really gained any advantage over classical computing yet. However, this will get you in the right direction. And the first thing that we have to think about this is, what about a superposition now? If we have a superposition, so we put the first qubit in a superposition of 0 and 1. It could be 50-50 just by applying a Hadamard or some other kind of combination. It doesn't really matter. Then what we get in the end by performing the control is actually not this output where you would assume that the two qubits are separable. The moment we put them in superposition, anything that is actually connected to it in some way becomes entangled. So here we have an entanglement that forces us to reason about certain combinations of outcomes. So in this case, if we think of A, B, the sum, and the carry over here, then what happens is you end up with two possible outcomes that fix the relation of qubits. So other combinations are not allowed. And that's the result of entanglement. We cannot unentangle in this case. And that's the interesting part. Okay. All right. Looks like you're answering your own questions on Slack. That is actually excellent. When we use qubits, we sometimes introduce temporary qubits. Let me see if I had a good example of that one. Here, these extra qubits are sum and carry. We actually use them for measurement. But in this more abstract quantum circuit, I had an S0 and an S1, and as you noticed, they were actually not measured. So I used them for some other purpose, which isn't obvious here from the circuit, but these are so-called ancilla bits, and sometimes I need ancilla bits to realize a certain operator to transform my state into yet another state. Even though I may not measure these, I need these ancilla bits in the middle of calculation. And so what I may start out with is, for example, a building block, like similar to our block that we had over here, which was a Toffoli gate, where we condition the third input to be 0. So our output was an AND between the two inputs, N3 and N2. So if I now want to create not a two-way AND, but a three-way AND, how would I actually do that? Or even a four-way? Well, I could use the same Toffoli gate again, take the output of the previous Toffoli gate, and then add another qubit over here as an input. That's my third input. Condition the third qubit input of the Toffoli gate again to be 0, so that it is an AND as well. And as a result, on that particular qubit output, I would get this one here. So it's now a three-way AND. I have another one, make it four-way. So in the and you can make it n-way essentially. Then you have an n-way AND. So it's basically an AND over all the n-i's that you have over here. And that would be your outcome. Now, what happens is the qubits that are marked in red circles over here have changed their state. And they're no longer 0. So if I perform some other calculation afterwards, I would have to factor in that they actually are a complex state that depends on the input states. But sometimes I want to reuse these bits here. These bits were essentially what's called ancilla bits. I use them just as temporaries to store some value, because eventually I'm really only interested in this value down here. Now, if I have a more complex circuit and there's some other calculations that come afterwards, right here, I may want to reuse these ancillars. And when I want to reuse them, they need to be in a known state, typically in a 0 state. So I could do that by uncomputing. And uncomputing means I have to perform the inverse, pardon me, the inverse operation to uncompute. So to uncompute exactly those things that are not 0. So I end up with 0. And I can do that because Toffoli is actually its own inverse. So I just put a Toffoli on here. And just basically uncompute in the opposite order that I computed. All right. And that will guarantee, because these are the inverse, that these two circled qubits over here are 0. And I can subsequently use them for some other calculation right here. This is important because qubits are actually scarce today, in the sense they're very expensive. real estate on a quantum computer. You only have few of them, and you have to make do with whatever few qubits you have. So reusing them is essential to actually fit algorithms onto quantum computers without, I'd say that in a more colloquial way, without declaring additional variables, excessive number of variables. So I'm basically reusing my memory over here in some sense to perform calculations. All right, and this generalizes, of course. If I just use the inverse, all I need is a reversible circuit, and then make sure that I use the opposite order to uncompute. And given a generalization of this, any classical circuit with T steps and S bits can be done reversibly in this O of T plus 1 epsilon steps and O of S log T bits. That doesn't mean it's the most efficient way, but it's one way that you have a method where it generalizes. Okay, I already talked about why uncomputing is important, so let me actually move on actually with a summary of quantum circuits. With what we've seen over here is any computation with an efficient classical circuit has an equivalent in a quantum circuit. So we certainly get all the computational power of classical computing with quantum, and we use reverse computation or to unentangle and to reuse ancilla bits within the computation. So I should go back and actually make that clear. As we uncompute, we also take care of entanglements when you perform the inverse. Then you also unentangle bits that were prior to that in an entangled state. And in general, qubits will be entangled with input bits, and measuring a particular x will collect the output of the corresponding f of x. So it's affecting the, in this case, the f of x that we have defined as our u of f in the above circuit. All right. So let's put this into IBM Qiskit. Qiskit is their Python-enabled embedded language. And actually, before we go there, let me show you something. Where do we have it here? Whoops, what happened? No, this wasn't it. Here. When you go back to the tutorial page, the web page, under sites Google.com, and you hit the info part of the page, look at the information over here. So we've covered the introduction, the foundations. We're now at quantum gates and circuits. And what you can do is, if you want to, you can actually install Qiskit and sign up for the IBM Quantum Experience if you want. Signing up for the experience initially is not important. It's only important if you want to run on a real device. I'll show you real quickly what this would look like. And enabling Qiskit is something, if you click on the IBM Quantum Experience, then you'll get some information over here. You can actually launch this, or where is the, let's see, wasn't there one? I think in the resources, right? Is it under Qiskit? I think so. So, whoops, why is it not going? Okay, I'm not sure why this is not going to. Not sure. I may have to do this on my other computer. Yeah. So typically you'll have to sign up for it first, and I've already done that. You could create an account if you want to, and then actually install Qiskit on your local computer. It's a Python package, so if you essentially just type pip install of the package name, and let's say Alice, maybe you can post in the Slack the install steps that are needed in order to get that package installed. And then another thing that you might need if you want to actually try this out yourself is the Jupyter Notebook support for your web browser. So if your web browser has support for that, you can also look at that. Let me see. So yours will probably look a little different than mine. Let me bring this over here and quickly share this screen. It's a different computer that I have to go to in order to do that. So if you actually sign up for Qiskit, yours will look like this. I just signed up with an account, essentially, an arbitrary account. So I have no special privileges. Just anybody in the world can sign up to use the IBM Quantum Experience. It'll eventually get you to this page over here. And what you see on the right side is a bunch of different machines. This one has 16 qubits. This one has, 15 qubits. One is not working, I guess. 5 qubits with different number of jobs in the pipe. So you see there's IBM Burlington, which doesn't have any job. We could run something on there right now. It would run right away. And let's see, how did I? If you go to the resources, it tells you how you can actually set up the Jupyter Notebook to run. And that's something we're going to do in the following examples. So feel free to do that on the side. And then you later on have many resources like the Qiskit notebooks. I'm looking for the install instructions for Qiskit itself. But let me just show you the other part. If I click on my account, it will actually show me some settings over here. And the most important one of this one is if we later on actually follow the instructions that were posted on the Slack page over here. So you can follow these Qiskit install instructions. Then you see somewhere in the install instructions that actually tells you that there's a pip install Qiskit. If you get to that point, you're in good shape. And then if you have created a quantum experience, you have the ability to use these two Python lines, the IBM Q save account with my API token over here, requires you to use the token that, requires you to use the token that you actually were getting from your quantum experience account setting. And you could just copy the token over here and then paste it into your Python session. This will save the token once and for all, so that any subsequent time that you use the Qiskit and you use a real hardware device, it will automatically run on one of the IBM Q machines. Now, mind you, these machines are somewhat backed up. We saw that in the beginning, a bunch of different machines. Some of them run what looks like few jobs, but some of these jobs can take, half an hour, and so on. And typically, you'll just have to see which ones are currently available. All right. So let me rearrange my windows over here and go back to the other session. Wait a second. I want to share the screen here again. And right. So while you're looking at Qiskit and maybe installing it, if you don't install it, don't worry, you'll just see what I run in place. Hang on a second, why? Me just look at what's going on here in Zoom, the Zoom settings. Okay, that's fine. You will see that there are different components of Qiskit. There's a Terra component where you can compose programs, and an Aqua component that actually is for building algorithms and applications, an Air component that includes a simulator. We'll use that, as well as emulators and debuggers. Why is there a debugger? I told you debugging is not possible. Well, if you use a simulator or an emulator, you can certainly debug it, because you can actually stop your algorithm at any point in time while it's running and look at intermediate state without collapsing it, because you're not actually running a physics experiment that will destroy superpositions. But if you run on a real device, then you're not using air, you're using a real IBM Q device, and it will actually destroy superpositions. So the problem is that the simulators don't scale up to many qubits. Otherwise, we could just run really large simulators. But obviously, if we can simulate something with classical computers, then there's no advantage to quantum computing. So the real advantage you get from larger machines with more qubits. And then Ignis, which is a error and noise level, essentially a module that allows you to go to the very bottom, very close to the hardware, and perform manipulations. So we'll focus on Terra over here. Terra allows us to build circuits. And what you need for that is registers and gates. And then you transpile or compile, which means you're translating to a quantum assembler, open QASM to be precise. And then that representation is transpiled down to backend instructions. So backend instructions are specific to a device. It would then take into account specific timings, qubit layouts, and so on that you really don't want to think about in the beginning. Maybe later if you learn more about it and you care about why you get noise. Then you have backends, and the different backends are the simulators, of course, within Air, or the real hardware. So what do we need? To build a circuit, you will need quantum registers. It's just a bunch of qubits, basically, that we index to get to qubit 0, qubit 1, and so on, and a set of classical registers. So the set of classical registers is typically the registers that we want for measurement. And it may be a subset of the quantum registers that we later on, the qubits that we want to read out. So only for those will we need classical registers. A circuit itself will be the set of registers, quantum registers, and then a set of gates that we specify as we manipulate state. So concretely, this looks like that. We perform some kind of imports for packages from Qiskit that allows us to first have 3 qubits, We call them QREGs, 3 classical registers, and then we combine them in a circuit. And once we have such a circuit, we perform a measurement. There's a little bit more code missing, but that's the idea over here. So you build a circuit, and then you measure, and as a result of the measurement, you will see your C-regs, the classical registers, and you can print them out at this point if you want. Now, we've learned about different gates, and all of these have a Qiskit equivalence. There's actually a Qiskit Python class that corresponds to these gates. There we go. So for example, an X gate is, let's say QC is my quantum circuit that I've created. Then I can perform an X gate on quantum register 0. Or I can perform an H gate, a CX gate, CCX gate, and so on. U1 is one of these universal gates where you actually specify an angle for a rotation. Measurement is also pretty straightforward, so it will perform a measurement on quantum register 0, destroy any superposition, and give us the amplitude in classical register 0. And reset basically means is you're setting it back to 0. That's not a traditional gate, that's just a mechanism. It tells the transpiler what to do internally. You can perform this on individual qubits, 0, or on an entire set of qubits. So here I'm saying if I declared 2 or 3 QREGs, then I'm performing an X on each of them at the same time in parallel. These are 3 X gates or 3 H gates. There are also meta operations or circuit operations. One is a barrier. A barrier just separates in time during circuit execution a set of prior gates to subsequent gates. And I can specify that a barrier be constrained to a certain subset of qubits. I can add additional registers to a circuit midway. I can combine a circuit with another circuit that essentially appends one circuit to the other and returns the concatenation of them. And the extent is one that actually performs an append again, but modifies QC. So it's a variant of the combine. And QASM will actually return the string containing the QASM representation of a circuit. So if I'm interested in that, I can look at what a circuit actually looks like in terms of the primitives at the assembly level, that is. All right, so let's go ahead and try to create this simple circuit over here that you see on the right side. We have 2 quantum qubits, and we want to set 1 into a superposition and then perform a C0. So you may remember, set a name. This is a building block that when you combine these 2 gates together, you are performing a state preparation of a so-called Bell state. And the Bell state has the property that you have a superposition with an entanglement. If we then measure, what would you expect? Well, let's see what we would get for such a program. So let me actually go to my other machine again. And let's see. We are at this point over here. If you go to let me actually before I go here. If you go to the web page that shows you, give me 1 second here. I gotta, since I see this, I gotta perform one change over here to our webinar. If you take a look at the web page, you will see that there are different examples over here under the Jupyter Notebook experience. If at this point you have an installation of Qiskit and you have Jupyter Notebook support within your laptop, then you should be able to take that example over here and pull it up in Jupyter Notebook, which would look exactly like this. And I'm going to enlarge this a little bit. It looks like it's pretty small. I think now it's easier to read, I hope. So, oops, what just happened? Not what I wanted. Okay. This is essentially what we always have to start out with when we use some kind of a Qiskit program. We need to have the quantum register, classical register, quantum circuit. I'm going to add to that air and execute because we want to actually execute inside a simulator, and also a little bit of visualization, which allows me to take the amplitudes that are part of the output and put them into a histogram. But really, it's only the first line together, maybe with a second line, depending on where you run, that's needed over here. So what we want to do now is we want to create a Bell state with a C0 and then draw the corresponding circuit, right? I mean, that was the task to be solved over here. So in this particular case, how would you start? What is actually a solution to this exercise? Well, you already saw that inside the slide. What I need to do is I need to perform a header mart on the first qubit. So I can just basically perform a header mart on qubit 1. And the first qubit, so this is kind of interesting, you need to know this, is the one that logically is actually the higher numbered qubits are printed above. We'll see that in a circuit diagram when we print it out. And after I've created a header mart gate for qubit 1, I perform a control not CX on, well, what's the control bit? So the control bit should be the one that I just changed to a superposition. So it should be Q1, the one that the header mart was applied to. That's the controlling bit, and the one that we are and the one that we are affecting is Q0 in this case. Oh wait, I just noticed I forgot to declare these. So if I was to later on execute this code, this would probably not work. But let me finish this. So what I wanted to do over here is what I wanted to entangle these two qubits over here, and then later on measure this. Unfortunately, we forgot to create some registers, and I haven't executed any code. I'm just editing in my notebook these different fields right now. So what I forgot is, well, I need to create registers over here, right? So I need a couple of quantum registers and put them in Q. That's where my Q1 and Q2 below comes from. And I also need classical registers. And again, 2 of them because I want to measure both of them. And you can see later on when I perform a Q measure, I will specify the QC and the Q and both C inside the measure. The other thing that I need to do is I need to create a circuit. My QC itself is a circuit. And I also didn't have that. So let me put that in there. I want a quantum circuit of, well, the quantum registers and the classical registers. All right. So since I have installed Qiskit over here, and I have the Jupyter Notebook, let's see if this works. If I hit Shift Enter, it should execute this. And it shows that now that I have a star in my in over here. Whoops. And it tells me I made a mistake. Oh, because I cannot spell. Okay. I can fix that. Classical register. And I just hit Shift Enter again. And in this case, it executed properly. And now we already have our circuit over here, the H and the CX. What we want is to actually draw that circuit. So the QC draw would print that circuit, as you can see over here. In this case, you can see that we have a header mark. So the circuit is printed the other way around, as you can see. It doesn't really matter. What we're interested in the end is a header mark with a control on the header mark side, followed by NOT that is applied to the bit that is being controlled. Okay, I could have changed the zeros and ones. It doesn't really matter. And what we want to do now is we want to actually measure the outcome. So when I perform a measurement, I will actually now run the circuit. So far, I've only drawn a circuit. I've specified the circuit. Nothing has been done with that circuit. The measure will compile the circuit. And if I have hardware, then transpile it and get the low-level transpilation sequence of operations ready, or otherwise leave it as at the OpenQ ASM. And when I finally get to the point where I want to run something, I have to specify a backend where I'm running. So if my backend is a simulator, I will just run these operations inside the simulator and run them repeatedly. So what does it mean to run repeatedly? I get multiple experiments. So in this case, it's 512 shots. Because I'm running a simulator, so even in the simulator, what happens is when I measure something, I collapse my superposition and the entanglement that I created and get a discrete output, a single output. Now, I don't want to get just one output. I want to get multiple outputs because I know for that particular circuit above, I should get an equal number of 0, 0 and 1, 1 states for the 2 qubits. And I should not see any other state. All right. So let's do this. Let's actually, when we perform the execute, it goes off to the simulator or to the real machine, and it'll run for a moment. And when it's done, so this call will actually block. When it's done, then it goes to the next line, and we can actually look at the result and do something with the result. So we can just print out the counts of outputs. So how many different outputs did we get? We should get 512 outputs, but for different states, different numbers. And then we can also print a histogram. So let's do this and see what happens. And lo and behold, with a simulator, that's kind of nice. We get what we expected, more or less. Because even the simulator simulates some noise inside. So it's not a perfect 50-50 distribution of the number of shots. We have 270 shots that are actually 0, 0. So there's more 0, 0s that we measured. And 242 that are 1, 1. And that's not atypical. When you run on real hardware, you may actually find this more skewed. And it could even be that you see a few single-digit shots results of a 1, 0 or 0, 1 state, which really shouldn't happen. But that means that something essentially went wrong. It was a noisy run, and the entanglement broke. The superposition didn't get established properly. Anything is possible. So this is reality when you actually run something. Even inside the simulator, you see a little bit, but the simulator still is well behaved in the sense that I only got correct results. I got nearly the same number. It's like essentially running a random number generator, and you see this random number generator wasn't perfect over here. Okay, let me actually pause and refer to Slack. Bappy asked, can a pointer to the web page containing the example be posted here? So we have that actually posted, I believe. If you go to the very top, where was it? Onka, I believe, in the beginning, had on the, where is it? Right here. At 9:13, a post that had the site's Google Doc link in there. So please scroll up on Slack and you'll find it, okay? And I think Dong's question should be answered what I just said. Yes, there is a noise model in the simulator. There are simulators without noise models as well. You have different type of simulators that you can choose from. Maybe we'll get a chance later on to actually look at that. So let me return to my slides at this point. This is where we were. And we are now continuing to, well, what we just saw. We can compile and run, and there are backends for simulation or the real hardware that I skipped over at this point. Maybe we'll do it later on. Let me take a quick look over here if I have a good example that we can maybe later on put a hardware run in there. Well, we could have done it for this one. Maybe I should real quick. Switch back to what we had. This would illustrate one other point. What you can actually do is you can use your notebook over here, your Jupyter notebook, to make some modifications and run it again. If you've worked with Jupyter Notebook before, you probably know this. But how do we actually now change our program to run on a real machine? Well, assuming you've signed up for the IBM Q experience, what happens is we have to use a different backend. So depending on which backend we want to use over here, and I have to remember now, let's see, I have different accounts with IBM Q. I think this one is running with the IBM Q hub that we have at NC State. So what I need to do is I would first load my account data, which would pull in the token that I already saved. And I'm not sharing with you because you're going to have your own token. You better do. Everybody gets their own token for their own account. And then I would put in a provider. So in this case, I run in a certain context. Your context would be a different one. So yours may look like more like, so let's say you guys are running on, I'm going to put this into a comment, London. So you would probably not have to provide a hub and group and project and all this. You would just put in a hang on, I didn't do this right. You would put in a provider that looks like this. Whoops, that didn't work. So for you, it would be IBM Q, group is open, project is main. For me, it's different. I have to specify different values over here. And I'm also going to use a different machine, hoping that this machine is available. Let me quickly switch over and make sure that's the case. How's Valencia looking? Usually it's not used very much. Whoops. Oh, let's see it right now. Manchester, Paris. Where's Valencia gone? There. Oh, there's somebody ahead of me. So Orange is open right now. I'll use Orange instead. It's always a good idea if somebody else is using it, just find an empty machine. How do you spell this? Okay. And let's see, when we execute, we now perform a job execute. We can still do the job execute as before with a different backend because we are no longer using the simulator over here, as you can see. Everything else stays the same. So let's run this. When I run, I have to go to the top again, run the first, the second, the Q measure. And now I'm going to load the IBM account, and it says something is wrong. Oh, I don't have the IBM Q defined. Yeah, I forgot that when you run on a real machine, you of course have to change your where is it? You have to change your imports. You actually have to bring in Qiskit as well. The IBM Q part. Let's do this. We don't want air to execute. We want the IBM Q to execute over here. So that's the equivalent line essentially. No, it doesn't work anymore. Whoops. There it is. Okay, let's start all over again. And it's going to take a moment to run right now because we're actually going out to the real machine. And boy, that's the demonstration effect. What is going on? It says I misspelled the backend. Orange is not found. Orange, not sense. I don't know where that came from. Credentials are already in use. That's not good. I may have to wait a moment before I can rerun this again. This is something with the IBM accounts. Okay, looks like it's now working. So that just gives you an idea with 4 or 5 lines changed or so, you're actually running on a real machine. And while we haven't seen the output yet, I'm still waiting for that one. You can see by the star over here, it is actually still thinking, still blocked on the execute. I'm not sure what happened there. Maybe somebody else is on orange ahead of me. Oh, I'm not sure. It doesn't look like it. But eventually it should come back with a result. When it does, I can share the screen again. Meanwhile, let me go back to our tutorial slides and share that screen again. So as we saw, you get some execution and some output that you can then depict in different ways. You have different backends for compiling, executing that you have to specify. Of interest to us are, well, the QASM simulator, and you can specify if you want a non-noisy or noisy machine over there, how many shots you want. Then there's a state vector simulator. So that is entirely different. And that's just using the simulator to create that vector psi that is the output state of all qubits with all the entanglements in there. And if you wanted to, you could use that for some kind of mathematical analysis using your favorite linear algebra library to inspect it, see what happens, and so on. You also have a unitary simulator that returns a matrix, the unitary matrix that represents your entire circuit. So if you have many different execution gates that you're executing, they will be combined into a single unitary matrix. And again, you can use that together maybe with some linear algebra to reason about your circuit in some other context with other tools. Then you have the IBM QASM simulator, and that's the QASM simulator that we that you would run at IBM where it's hosted. It's a different version of the QASM simulator above. It's one that actually scales up to more qubits and then has server-side execution, but they don't release that code to everyone. So on the hardware side, you have the IBM Q providers that we already saw. We saw some other operational features. So you can look at the status of a job and check if a job is done, check on the ID, the result. The result is what we looked at. And when we use get counts, for example, we were actually seeing different number of shots here for a 3-qubit entanglement that was probably run in a QASM simulator without noise because it's so perfect. And job monitor is actually a loop that waits for a job to complete. You have that as well. All right. So when we ran all this, you saw we got some number of zeros, some number of ones, similar to this one in our case. And we could now go to the next level and essentially ask what happens if you take some other circuits and run them through. So if you take some other circuits, what would be the result? What would you get in this case? And while that may be of interest over here, keep in mind that, well, I mean, we could go through that real quick. What would you expect as an output for that one? And that's actually an interesting question. So we have a 3-way entanglement that results from 2 superpositions that we're creating. And this is the example 2. If you want to, you can actually look at the example 2 and see what happens with that one. So let me actually go back and look at the Jupyter notebook for this one. And for that, I'll have to switch over to the other screen again, which, by the way, we just received output from our hardware. So that was a live run on the IBM Orenz machine. And what did it give us? Well, as you can see, it also gave us 512 shots, but now they are distributed a little bit differently. We see fewer 00s than 11s, and these 2 sets still make up the majority, but there are a few 9 shots of 0, 1 and 10 shots of 1, 0, as you can see right here. So the noise on the real hardware is a lot stronger than the noise that's being simulated, as you saw before. Maybe not surprising, but that's what it is. So, whoops, what happened here? I know what happened. Let me get rid of this. If we now want to create our second example, the CC knot, so it's a Toffoli gate, what would we do? Well, it's pretty much straightforward. It's similar to what we did before, in the sense that I first have to create my classical and quantum registers. So let me go ahead and do that over here. I need 2 quantum registers. In this case, it's actually enough to have 1 classical, because I just want to see the output of the 3rd qubit. And then I can entangle and Hadamard these gates. So let's see, I want a Hadamard on, say, whoops, that didn't work, on Q0, and I want another Hadamard. Let me just copy that. Whoops. On Q1. And then I want to perform a C knot that's controlled by these 2 qubits and has a target bit Q2. All right. And that will create a 3-way Bell state. It's a 3-way entanglement, which I subsequently want to measure, right? Okay. So let's say that's what we want to do. And let's execute that. So far, so good. Now we're going to draw the circuit. And it's just what you would have expected. And now I'm going to use the same simulator backend, which has some noise. And we measure as an output 0.75 and 0.25, roughly. So what does it tell us? Well, we now have to reason about that output again in terms of the original circuit that we had, which had the 2 Hadamards, so the 2 superpositions. And because you get a 50-50 with a single, I mean, with 2 qubits, just a single Hadamard and a Bell. So what happens is, if we, in this case, just reason about the output of the 3rd qubit over here, that 3rd qubit will now be conditioned by the combination of the different states that we get in this case, right? And you can actually, oh, sorry, I didn't do this right. So if you later on think about how many combinations of these will actually result in the valid ones, then there's 3 combinations that, because of the entanglement, will result in a 0, 0 for the first 2 qubits, and only 1 that results in a 1, 1 for the first 2 qubits. These 2 qubits are driving the output of the third qubit, so that if the first 2 qubits are 0, 0, my output of the third qubit, Q0, whoops, Q3, I should say, would be 0, whereas in this case, Q3 would be 1. So this is actually where the 75%, 25% is coming from. All right. And no other output should be expected here. All right, so here we have another challenge for you. Can we actually implement a circuit checking if 2 qubits are equal? Okay. And that's the third example that we have here. If we go to the Jupyter notebook for the third example. How did that happen? Okay. Let me share my screen over here. So if you loaded the third example, it should look somewhat like this. We again have our imports as before. We create a couple of quantum registers, a third quantum register for the output, a classical register, and combine them in a quantum circuit. And what we next want to do is define a function that implements equality. So it's checking if 2 qubits are equal, the 2 qubits that are part of the input, and then asking us to present that result in the output. So how could I possibly do this? Well, if you recall, we already had essentially a very similar circuit that we learned about. We had a half adder circuit that was actually combining the first and second qubit to create a sum and a carry. And if you have 2 qubits that are equal, then you can use a C0. That's basically just providing the sum. If you can use a C0 of the 1 qubit on the output and a C0 on the second qubit on the output. And what we've done now is we've basically added these 2 qubits together. So if they both were 0, then our output would be 0. If they both were 1, then our output would also be 0. With adding together, I mean adding together in the half adder sense, because our carry would be 1. We don't need a carry over here, but our carry would be 1 if both input 0 and input 1 were 1. So instead, what this circuit so far, the 2C axis, gives us is a 0 in case both inputs are 0 and a 0 in case both inputs are 1. Well, we want actually the output of this circuit to be 1 whenever the inputs are equal, which is the opposite of what our current output is. So I can simply negate the output or perform an X, a not, on the output. And then I have implemented an equal circuit. I hope this makes sense. It's kind of hard for me. Let me actually see if there's anything on the questions. No, looks like there are no questions over here. No additional questions, and I hope the other ones about how to install Qiskit have been answered. If you can't get it working right away, don't worry. Maybe take a look at this after the tutorial's over. You have access to all the materials, and then you can walk through these examples one by one again. Okay. So what we now want is we want to use this function. We've defined a function that will abstractly take 2 qubits and produce as an output a third qubit, and tests for equality of the 2 input qubits, and should give us a 1 on the output. So we can test this by now calling this function and then performing a measurement. So I just call the equal to on the quantum circuit for Q in and Q out, which will then apply the circuit over here on first CX input 0 output, input 1 output, and then circuit X on just the output, which is really the circuit is QC in this case. And then we measure. And after we measure, we simply print the result as before. So let me run this through the simulator real quick. Here we have our circuit, as expected. And when we look at the output, we see that the output is 1, which means that the inputs were the same. When you look at the circuit, you will see that the inputs to both Q0 and Q1 over here are 0. So they were equal, and our output is 1. I could modify the circuit to change the inputs if I wanted to. For example, I could set one of the qubits to 1 just by performing a NOT operation, an X. And now I would have to go through the entire circuit again. When I print the circuit, it looks different, of course. You see that Q1 now has an X in there up front, which changes the input to the equal circuit being the final 3 gates, such that one input is 0, the other input is 1. So we would expect as an output 0. And indeed, we get that output. And by the way, we get this output in this case for every single shot. So even with the noise, I don't have any problems. You can see that the noise has more of an effect when Hadamard's are actually in the circuit than in any other case. All right, that said, let me return to the slides over here. And there was an interesting question over here on the bottom. Would this circuit work to test whether 2 qubits in arbitrary states are equal? So in arbitrary states means, well, what now? We would have to actually reason about, for example, a Hadamard on qubit 0 and qubit 1, which gives us an equal superposition. And then we would have a CC0 to fully that performs a control on the final bit. Well, what do you think? Should it be working still, or would there be a problem? Well, if you think about it, it's actually very similar to what we have looked at over here, in the sense that what we're doing is we have a header mark, in this case, with one qubit and a second qubit. Here we had a Toffoli. In the equal, we just had two C naughts in sequence on the initial bits being the control bits for this, each of these gates. But the problem is that after the first one, I start to entangle the third one, and then I start to entangle the second one. So I'm already starting to affect them. So I'm not really testing for equality anymore. And this is really something else. And that's also the strange thing about quantum circuits. You always have to think about the states that you're in. And if the circuits that you're designing from the logical point of view make sense. So I've gotten to the point where we've created circuits using quantum classical registers, then added gates and measurements, chosen a provider and a backend, and then executed this circuit both in simulation and on real hardware to then interpret the results in terms of their amplitudes. In reality, when you go to a real machine like the one that we saw, we will actually see that machines have limited connectivity. This means that you have qubits here depicted, for example, if we look at the first one, it's a machine that has 20 qubits. Each qubit is connected to one or more other qubits, sometimes as many as 3. And this means that you can perform a C0 between 0 and 1, but not between 0 and 5 or 0 and 6 or 0 and any arbitrary one. The limited connectivity constrains you in placing a concrete circuit onto the hardware. When I have C0s, I now have to search where qubits are actually connected and make sure that I choose adjacent qubits in the mapping from the logical qubits you declare in your program to the physical qubits on a device. If I end up with too many C0s that I need to be adjacent, so for example, for some reason I use all 20 qubits and I decide that qubit 0 needs to not only interact with 1, but maybe also with 5, then I have a problem. And the problem can be resolved as follows. What I can do is I can take qubit 0, perform a swap it over to qubit 1, if that one is available, or that actually it's no problem. When I swap, I take the value of qubit 1 and move it into qubit 0. So it's a mutual exchange, right? So now my virtual qubit 0 from my quantum circuit in Qiskit sits here. I can do the same thing down here, move my virtual qubit 5 to 6, and now these two can actually interact. And once I've performed my C0, I can actually swap them back. And the interesting thing is, after I swap them back, they're still entangled. Unless I unentangle, they remain entangled. So they don't need a constant connection to remain entangled, of course, within the limits of decoherence. And depending on the different backends, you have different connectivities. Some are more dense than others. This will constrain you in your programs and also add a lot of swaps when your programs become more complex. Okay, so let me, in terms of the bigger picture over here, quickly look at where we're standing. I think this might actually be a good point to pause for a moment before we go into the more complex algorithms. I know I'm a little bit off the timeline right now, but it doesn't really matter. So let's take a quick break over here and come back at in 15 minutes. So that would be 1:40 my time. All right. Let me actually make a mark on the slide. All right, I'll be back. All right, welcome back. Let's continue with the gate-based programming by looking at what's happening over here in terms of quantum algorithms. So we're going to look at slightly more complicated circuits that give us the potential for a quantum advantage, the potential to actually make a difference to classical algorithms, unlike some of the simpler examples that I've shown you. And all of these will have in common that they have some kind of superposition in their circuits. In fact, part of it is to reason about quantum parallelism. And the parallelism is here. One, don't think so much about circuit parallelisms and the different lines for qubits, but rather the state parallelism, the different states that are being represented in a quantum computer. So give me a moment. There seems to be a problem over here with my projecting capabilities on the other device. I need to get back to. Give me a moment. There seems to be a problem over here. I need to get back to these slides, but this requires that I log into Zoom again. For some reason, it kicked me out. It's bad. I need to do that. Okay. Let's get back to quantum parallelism. Let's assume that you have a typical transformation. This is just some function, some unitary over here for a function f. And all of the following examples have in common that we have an input that typically is n qubits. And most of the time, you'll get the same n qubits out of the unitary function. And then you have some additional qubits, m of them, that somehow combine with a function that is actually a input that takes x as an input. And they combine on the m qubits, the lower m qubits. What we want to do is we want to reason about what happens if the function or the unitary transformation, the operation is actually performed on the superposition of states, states over inputs where we have superpositions for the x's and then zeros for the y's over here. As a result, we get out some states x and f of x. So it could be this combination, or it could be some other combination that we want. But if we're going to measure, the problem is we're only going to get one value because everything collapses. So if we want to somehow keep the superpositions alive, we have to think of some other tricks that we can use in this case. So first of all, what we want to do is create superpositions. And then a typical technique is actually to somehow select values we're interested in that, in these values. And for these interested values, we actually amplify those values and damp or diminish, reduce the other values in their amplitudes. And we have the ability for amplitude manipulation through the different phase angles in quantum. So this was actually discovered in the 80s and was one of the breakthroughs to make quantum algorithms feasible and also interesting beyond what you can do with classical. What we want in the end is get highly amplified values with high probability. That means many shots should give us this value back that we're interested in. And then we can still repeat the experiment multiple times to somehow learn more about the properties in an algorithm. So what this means is we may actually run our quantum algorithm, then run a classical algorithm, use the output of the classical algorithm to condition the input to yet another quantum kernel, and run the classical algorithm again, and go back and forth multiple times to then narrow down some desired computation, some desired result. And the measurements that we have, of course, help us in getting there. So let me give you one example, one of the first examples that actually discovered such an interesting amplitude amplification method, which is Deutsch's algorithm. The problem over here is given a Boolean function that goes from 0, 1 to 0, 1, so from Boolean alphabet to a Boolean, determine if f is constant. And what we want to do is basically, well, there's different functions for f. I can just write a function that always returns 0. I can write a function that always returns 1. Or I could write a function that, depending on the input, it inverts it. So those are essentially my options. Now, what I want to do is I want to generalize this to reason about whether this function is constant, this function f is constant or not. So uf implements f and is given to me. It's a black box. I cannot look at it. Maybe it's a constant function, maybe it's not. Here's the idea. We will first put the input state into a superposition of 0 and 1. So this becomes a +1, -1. So a superposition for x, and we need a different superposition on the second input, which initially is 0. And then we want to look at the f of x. And if f of x is constant, we want to see an output that's plus-minus, which means the plus over here refers to the x being in a superposition that's with a positive sign, and the minus refers to the second qubit in a superposition with a negative phase. And if f of x is not constant, we want the output to be minus-minus. So just take that as given. How you actually come up with this idea of requiring an output to be plus-minus and minus-minus, you'll see in the end why it makes sense. So what we want to do is you apply a Hadamard to the first qubit in the end. And I mean, after you're done with all this preparation, I just put a Hadamard gate right here. Oops, sorry. and then measure. I put a measurement behind that. The measurement will reveal what happened to the first, to the upper qubit. Is it a plus or is it a minus? And will, in accordance to that, give us a 0 or a 1. 0 if constant, 1 if not. Now, the cute thing about this algorithm is it's actually more efficient than classical. Not by much, but it will be the building block to larger similar algorithms. So why do I say this? If I want to check classically, what I would have to do is I would simply have to try out. I'll perform an f of 0. I'll perform an f of 1. I'll compare the outputs, and I see if the output is constant or not. So it's 2 calls that I have to do. And the claim is, if I properly condition a single quantum circuit, I only need to run once, and it will give me an answer whether or not this function is constant or not. Again, this is, of course, in an ideal quantum computer, no noise, but let's assume all that. So how does this actually work? Well, assuming that you have, and let me actually go back. So we wanted to start with an input state of plus minus. That's what you see right here on top. And then apply our function, that is that black box function. So what this means is we want to put the first, how should I put this? The upper qubit, first qubit, into a 0, 1 state with a positive sign, and the lower one in a 0, 1 state with a negative sign. So I've actually pulled out the 1 over square root 2 terms and multiplied them already together, as you can see. And now by linearity, I can express this first line in terms of, and this is the interesting thing, an XOR operation for the value 0 and F0. Okay, because we are now pulling in UF. Sorry, we're just pulling in UF. The linearity comes in the next case. So we are pulling in UF and performing an XOR on the 0 state or on the 1 state of the respective qubits, which we can then combine by saying, okay, what we really have over here is 2 terms, these 2 terms over here and these 2 terms that do an XOR with 0 or 1. They have common sign, but then they need to be combined with whatever my X state is. So what is my X state? That's actually the input to the first qubit, which is also coincidentally what my function takes as a parameter over here. And I have to do this for both possible values of X, 0 and 1. And I've pulled out the 1/2 over here. And that's again because of linearity. Now, when I consider what happens over here, in terms of when f of x is 0, what I get is, well, if f of x is 0, then essentially these terms collapse to just a term where I'm left with the 0 minus 1. Okay. And that's exactly the case that I have down here. So that's the minus superposition. Whereas if f of x is 1, then I get the additional sign in here, which is carried in the result. So I can write this as a 1 minus 0, which is the same as actually the minus cat with the sign up front. And the sign is what I'm interested in over here. So in other words, what I've implemented is essentially a function or a circuit that evaluates the function f in an abstract superposition state that provides the input. And as a result, I get a another state. So I still get the original x out, but in this case, I have the minus that you saw before, plus a sign, a potential sign, which is actually an indication for the phase that happens over here, which depends on the value of x. So if f of x is 0, this evaluates to 1. There is no sign. If f of x is 1, then this evaluates to -1, and I actually do see the phase shift of the sign. So I'm going to pause over here for a moment just to see if anyone has any questions. Let's see, where is that? All right. And take this one step further. So this is the equation that we had at the bottom over here. So just to get to the crux of it, when f of x is constant, clearly this becomes -1 to the 0, and you don't have a global phase, and the output is plus minus. And if it's not constant, this becomes a 1, and that is exactly the output negated, which gives us the ability to then perform a final Hadamard on this output. So the output that we get over here before the Hadamard was either a plus or a minus, depending on whether it's constant or not. And after that, we measure, and we get out a 0 that would correspond to the plus, which would tell us that it is constant, or a 1, which corresponds to the minus, and tell us that it is not constant. So that's the key over here. We have constructed these Hadamards that give us as an input to UF a plus, and on a lower qubit a minus. It's a minus because we had the X gate before the Hadamard. Remember, that projects it to the back on the block sphere. And we really are not interested in this output over here. We're just interested in measuring the upper qubit. That will give us the answer right here. Now, if you think that's hard to understand, I'm with you. It's not always easy to first get that. I'm going to give you a couple of other explanations in the following. And maybe the second one or the third one or any one of these three will help you understand what's going on. So another way to look at this, so the last one was more along the lines of Eleanor Riefel's book, whereas the following ones are explanations that you can find in David Merman's textbook. And so what he basically says is, look, if we're just looking at the simple, the simple function f for which there's two possible inputs, 0, 1, something in a binary, then what we want to do is we want to assume that a UF unitary actually exists that lets us transform this into a circuit such that the output of the circuit is still the input, and then y XOR f of x as the second qubit. What we in effect could do is we could take all possible functions that you see on the top over here. So this is a constant function. No matter what the input is, it will always produce a 0. This is a constant function. It'll always produce a 1. Whereas the other two functions are not constant functions because they have two different outputs and the output depends on the input. If I want to look at how to construct these different functions, I don't really know what's inside my UFF, but I'm just playing a what if. What if I already knew? What if I could look inside? What could it look like inside? Well, you basically come up with 4 different functions. F of 1 is implemented by the identity. You don't manipulate x. You don't manipulate y. The two qubits stay the same. And out comes the same value, which is implementing x and y XOR f of x. Now, if we wanted to implement F3, what would you do? Well, you essentially always output 1. So assuming that your input of y is 0, I just put an X gate on there, and I always get 1 out, no matter what you put in on the X line. If the input is 0, then you still get a 1 out here. If the input is 1 in terms of X, you still get a 1 on the bottom. So we don't care if you put 0 and 1 in here, you always get a 1 out. The same was here, 0, 1. Input, you always get a 0. Now, if we want to implement sorry, this was F0. I made a mistake here. If I want to implement F1, then what needs to happen is, based on the value of the input, whether it's 0 or 1, I want to perform a conditional NOT on the second qubit. And my output would be 1 or 0. So it's basically, sorry, I do this wrong? No, it would be 0 and 1. Would be the same. Whatever I put in on the top will be coming out at the bottom. And if I want the opposite to happen, this would be my F2, then I just put a NOT gate in front of the C NOT. And then my output would be 1 if 0 was the input, or my output would be 0 if 1 was the input. Just the opposite. All right, so I could construct these 4 different circuits and reason about them. But what I really want is to not put 0 or 1 on the X line and then look at what the output is, because that's still doing the classical thing. I want to somehow use a superposition on the input states to test both 0 and 1 as an input at the same time. And honestly, I'm just interested in 0, 0 and 1, 1. So I'm assuming that the second qubit is always 0. So if I want to create a superposition, then I just apply H, of course, as you would think. And I make sure that somehow I put 1 on the other line. And that would then, after I apply UF, give me the ability to actually look at, so this is square root 2 over here, the states for 0F0 and 1F1. That's actually what I'm interested over here. So instead of having 4 different circuits, of course, we have one circuit, and we don't know which circuit it is. So we somehow have to evaluate that with essentially Hadamard on both registers and NOT gate up front that we need. So what we do is we essentially take the original input state, which was both zeros on X and Y, transform that into a 1, 1, and then put them into a superposition. And when I actually do the math for all this, what this will do, this will essentially, so the X and the zeros combines into 1, 1. Then you take the 1, 1, put them in superposition, and you end up with this term after transformation. Let's see, did this look right? Yeah, so you have 3 different terms, 0, 0, 0, 1, 1, 0, and 1, 1. And all of them have, oh, I think there is, let's see, this should multiply out to be 1/2 in this case. So the square root actually may go away. Need to double check on that. But the point is, well, actually, maybe it still stays there. The point is, after we have that, no, I think yeah, it should already be removed because it actually multiplies out in the previous one. And now apply UF to the resulting state that we see over here. Then we actually pull in UF to the respective possible states. So we do this for each state. What UF does is, in effect, apply F on different values, on the input value. So the input value was either 0 or 1, depending on what one of the qubits does. And yes. All right, I need to fix a few typos over here. And then you also end up with the possible 0 F prime, where F prime is actually 1 XOR F. So that's the inverse of F, essentially, and 1 F prime, of course, for the respective values. So all of these are being combined in a single state. And when you have that single state, then what you want is you want to reason about first the fact that UF of XY is equal to X, YX, or FX. And due to that, we can now distinguish 2 cases. The constant case, where F0 and 1 have the same value. You can see that over here in the table on the right side, right? Oops. There. And in this case, what happens is there's only 2 terms left that we're interested in. We're interested in when they're the same, the 0 minus 1 and F0 minus F prime 0. So when we apply H to the input, that's basically what we get in this case. We get a 1 up front, and then on the other one, equal superposition on F0 minus F prime of 0. So notice the sign in here, that's significant. Whereas, if n is not constant, then f of 0 is not equal to f of 1. And what we end up with is a different sign over here, of course, for the 0 and 1. And that's coming from the second term in this case. And then you still have the f0 and f prime. And that's because f1 is equal to f prime 0, and f0 is equal to f1 prime. So in other words, we now have the 0 up front over here instead of the 1. And that allows us to distinguish the two cases. So if you paid close attention, you may have noticed that driving the output of this, the first qubit is the indicator in this case. So after we've taken the output of, say, this line over here, applied the header mark, is actually the first qubit that gives us the answer, but it's the opposite answer than in the first Deutsch solution. The first Deutsch solution, we had a 0 come out, the first qubit, when the function was constant. Here you have a 1 come out. So this is simply a fact to an extra X gate. It's equivalent in functionality. It just provides the inverse output. All right, so but when we combine this together, then we end up with essentially a header mark on the first qubit and one that we have on the second. We combine it with the output of UF and get these different values as the first qubit. The rest of it is just applying the preparation, the state preparations, and then distinguishing the different cases for F and F prime. So we're measuring the first input register to get a 0 or 1 on what circuit? Well, it's exactly this circuit over here. So you could actually try that if you wanted to. Let's see if we can. Let's see if we can switch over to a Kirk in this case. Let's see. I can show you a Kirk example. It's faster to do in this case. All right. And let's see if I remember this correctly. So we need to have 2 X gates, 2 header marks, and then we have our function in the middle. That's our abstract Q function. And let me choose a constant function right now. So one constant function was the identity function, as you may recall. So an identity function would just be nothing, basically. We're doing nothing. And then afterwards, we put an H up on top and measure the first qubit. If the first qubit is 1, it's telling us that the function that we've implemented is a constant function. Okay. I can try another constant function. That would be if I have an X on the bottom. If I have an X on the bottom, it will, for that function, always produce an output of 1. We don't see that output of 1 here because we're actually looking at the abstract value. So my UF is just this X gate over here and an identity gate on the top, which is not visible, but it's effectively an identity gate. So these are the two constant functions, F0 and F3. I called them on the slides. If I wanted to now have a non-constant function, I need a C0 in here. And if I put a C0 in here, oh, wait a second, it did not pull this one around. And why is that right now? All right, so let me see. Oh yeah, so due to the C0, you can see that when I put the control in there, my first qubit changes its state from on. You can see that's actually in an on state, green over here, to off. Now it's off. The off state indicating that it is a non-constant function. The other non-constant function we had was, I can put another x on the bottom. It doesn't change anything to the output. It's also a non-constant function. Okay, so that was the quick demonstration in Qiskit. A more complex one would be this one. You can now generalize this to not just a binary function, but an n-bit function. And our UF would be what's here in this const block. And if it's a constant function, then what we're interested in is actually seeing if in the end we get 0 or 1 over here. So again, the condition that I had constructed is version 2 in the previous Kirk example. This Kirk example here was, I think I called it version 2 in the slides. This is a version 1 which has the opposite output. So if the bit over here is 0, that means it's a constant function. If it's 1, it's a non-constant. When I want to look what's actually in this constant function, this is a building block that I created. You can create custom blocks for circuits, sub-circuits. It's just the identity. There's nothing in there. But I can swap this out, get rid, and I'm uncomputing here as well. That's why I used it twice. And take a balance function. Now my balance function, if you look very closely, when I click on it, whoops, it'll actually show me what's inside that function. And you can see it's C0s that go to the bottom bit, and all of them have a single control from the first, the second, the third, from each qubit down, basically. So if I put the balance function now in there, and eventually uncompute, then you see suddenly my input qubits that were 0 have become 1, indicating that this is a non-constant function that's inside my U of f. And this is really my U of f. This is my U of f minus 1 to uncompute, just to get the bits unentangled and then measure. All right, let's get back to set of slides and give you a third idea of how to reason about Deutsch's problem. There is yet another way. And I'm spending so much time on this because we will see that it becomes a building block actually to use these functions where you can somehow magically put something into superposition and then reason about the function abstractly instead of providing a discrete input. There was an interesting question on the message board where Bapi asked, what is superposition really? Is it more like concurrency or parallelism? Concurrency typically is defined as the potential for a program to execute in parallel. So you specify in a classical program the ability that certain sequences of instructions can actually be executed if there are execution resources that allow you to run this in physical parallelism. What you're doing here is different. You're not really running, say, the input value 0 and the input value 1 in parallel on 2 different processors. That's not what a superposition is. Instead, you're actually reasoning about the superposition, a combination of 0, 1, encapsulated in a single qubit that is evaluated in the context of some function over here, this u of f, for example. So it's a state parallelism rather than an execution parallelism. That's the best that I can describe that difference. And it's a subtle difference. It's a completely different concept. It has no equivalent concept in classical computing, because while I can have different state values, I cannot enumerate 2 to the n values with just n bits. But I can exactly do that with qubits. I can enumerate 2 to the n states, actually, and reason about them in n qubits. And that's the major difference over here. So the third way that we can think of Deutsch's problem is as follows. I gave you the idea that if we assume this u of f exists and gives us as a second output this y, x, or f of x, and we start again with the different functions over here, f1, f2, f3, f2, f3, f0, 1, 2, 3, then what we want to do is somehow abstract the evaluation of the function. And again, the intuition here was, in order to exploit the capabilities of our quantum computer, you want to essentially put all the inputs into superposition. And when you do that, you also have to uncompute later. So you want to reason about actually applying the Hadamard after again. So that's maybe fairly intuitive. And when I do this, the result should really be unchanged. I apply a Hadamard before, and I apply a Hadamard after. Except, and here's the interesting part, there are known equivalences. I introduced an equivalence earlier. It was a swap. Remember that the swap gate was equivalent to 3 C naughts, where the middle one is actually inverted. And there are other gate equivalences. So one equivalence is if I have 2 Hadamards in sequence, it's actually the same as the identity gate or nothing. If I have a Hadamard followed by an X followed by a Hadamard, that's equivalent to a Z. And in order to verify that, you can actually use linear algebra to look at the math, or if you prefer so, reason about the block sphere in these cases. So that's still easy to do for single qubits. But when you have multiple qubits, it gets more complicated. And here's one of the interesting ones. So when you actually have Hadamards before and after and a C naught in the middle, in the 2-qubit case, you have essentially an equivalent circuit that is reversing the direction of the C naught. And I'm pausing here because that's not intuitive. This is exactly where quantum is completely different from VLSI logic, or so. It's a completely different way that you have to think about it. You can verify this, again, as I said, with linear algebra. We actually looked at that earlier and verified also that you get a kickback effect. So it's often called a kickback. If you have Hadamards, Hadamards before a C naught and after as well, then you get a kickback effect where the lower qubit actually has an effect on the upper one. And that's exactly what this is saying. Hey, you're now controlling with the lower one what happens to the upper one. So let's assume these equivalences have been established. And once they have been established, all we need to do is use them. So how can we use them? Well, look at the circuits on the very left. We had this F0 over here. And the F0 was actually establishing that if our interior circuit, the UF, was F0, and we did a header mark before and after, nothing would happen, right? It would still stay the same. That's basically what it says. But if the circuit, and we can, well, we'll get to that in a moment. If we look at F3, so let's say our U of F in the middle here is F3, what happens now? Well, that's equivalent to this case over here. It basically means that we now have an H, then F3 is an X in there, and then an H. And nothing happens on the top, it stays the same, just a flat line. So it's HH. So that's equivalent to just a Z gate, that third example, which leaves us with F1. And for F1, I now have a control X in the middle of an H, which is exactly what this one is. That's equivalent to a reverse controlled C0. Or I get a reverse control C0 in this final case with F2 with a prior X gate. So there's an X gate in between the H's. That means I have a Z and then a reverse C0. So in other words, you see that I can get an H, and you have UF and H using these equivalences. And I end up with my abstract function to be equivalent to either this or that, which would give me for a constant function an output of 0 and 0, or an output of 1 and 1 on the function itself. And for the other ones, I get these two not constant values. And this will then result in, well, we have to think about this first. If the input is 1, then so the input to the function, I should say, is 1. Then the output X is equal to the, so no, sorry, I had this backwards. If the, oh yeah, exactly. So assuming that we actually start out with a 1 on the second qubit, then the output to X is equal to the input of X if and only if F0 or F3 are being used. So that's basically our constant one. And otherwise, you get the opposite on the input. So that means that you have a non-constant function. It's F1 or F2 that is being used over here. So in essence, you have an argument for thinking about this in terms of circuit equivalences that allows you to boil down this problem of constant, non-constant functions to one that distinguishes these two cases when enclosed by header marks and put into superposition. So that's kind of a cute way of thinking of it as well. Maybe easier for people that think about circuits as an abstraction. All right. So let me actually move on over here. There is another important algorithm that I want to look at. That's a selective phase change. So a selective phase change is a problem related to Deutsch's problem and will eventually lead us to Grover's algorithm, as you will see. So here you want to change the phase in terms of a bunch of qubits. You have a superposition, some state psi that's encoded by the different states summed up with their different amplitudes, depending on whether I is a subset of X in this state or not. So more specifically, what you want to is you want to find an implementation that's actually a transformation and separates these states into two sets. The sets where you actually have a state that is a member of a set, and those states that are not a member of a set. And what we are looking for is a transformation. So for this, what we need for this is some implementation of a transformation function, a unitary again, that tests for membership. And it's very simple. It's this function over here that basically says this function should return 1 if x is an x and 0 otherwise. Now, this is essentially an oracle, again, because we can't look into that u of f that implements our function f. And using this oracle, we can then enclose it again in heteromarks and reason about the oracle to discover some property of the oracle itself. So in this case, what we want to do is actually look at how many terms you, for example, have that are a membership case and those that are not a membership. So which x's are in big X and which x's are not. So what we do is you start out with a state of psi and 0. And then you apply u of f to it. So when we apply u of f to it, what we get is we pull in the function over here that f of x is now applied to our state x as a second part of it. So that is essentially distinguishing the two cases. If f of x is a member, x is a member of x, then this becomes a 1. If it's not a member of x, then this f of x becomes a 0. Okay. And what we can now do, and this is kind of interesting, we actually use a phase change gate. So here in this case, we have the phase gate U1. I use a U1 because that's actually what it's called in the IBM Qiskit case, and apply it to the output bit. So that would in effect be the unitary matrix that you see over here, where in the bottom right, you just have the phase shifted by this angle over here. Now, the phase shift itself does not affect any measurable state at this point, not directly, but it will do the following. So what it does is, let's say we have in this case here some inputs. So we're just essentially applying the identity on the n top qubits. And then on the bottom, we apply a phase shift. And that's based on some state. And the state is the state that we saw above over here. Now, rewriting this, what we're really doing is we're distinguishing membership. Those that are a member on the left side, and those that are not on the right side. Those that are a member we know that the last qubit is 1, but it will be phase shifted. And those that are not a member will not be affected and won't be phase shifted. So that's the crux over here. So why is this the case? Well, if you do the math in terms of the unitary that you have over here combined with the membership information, you actually end up exactly with this phase shift that due to linearity you then pull out. And what you end up with is the phase shift essentially being abstracted, and depending on the value of f of x, that could be either a 1 or a 0, it results in some phase shifts. So I can actually combine these phase shifts with the non-phase shifts and then make them dependent on a second qubit that's encoding my f of x, so that I get exactly the state that I wanted as an output over here, which is the state psi and the f of x. So what this means now is, after I'm done with the phase shift algorithm, the circuit, I would actually have to go back and uncompute, which isn't a problem, because assuming I have an inverse function for UF, I can remove any entanglement bit that I have and then take a look at the output and measure. So the output, and that's the interesting part over here, is in this case the n qubits on the top. That's very similar to Deutsch's algorithm, where we actually looked at the input bits being transformed, or input set of input bits being transformed, so that we look at them, how they were changed as an output, to then glean into the function u of f and make a reason about what internally is happening over here. So there's a special case in this case. When my angle phi is actually pi, then I can transform this upper circuit into a simpler circuit where W is the Welsh Hadamard. So it's a Welsh Hadamard that if you have n qubits, it's basically putting h's on there. Here it's just a single, depicted as a single qubit. And out then comes my state psi that gives us, and this is something that should look familiar, similar to Deutsch, it gives us a f of x sign. So depending, that's essentially a phase angle, a sign that indicates something about the membership that we were interested in. In those cases where we have membership, we would see a -1, and in those cases where x is not a member of x, we would not see it. Yeah, so let's actually do a Qiskit example at this point. So what we want to do is create an equal superposition. And let's just take 2 qubits. We can generalize that later if you want to. That's an interesting problem you can try at home. And then what we want to do is we want to flip the phase when the 2 qubits are equal. Okay. So let me actually switch screens again. And I hope that you can follow this example. It's a little bit more intricate than the other ones that we've seen so far. So where did I get this from? If you go to the tutorial page, we are now looking at phase. If you actually enabled the Jupyter Notebook together with Qiskit, you can walk through this together with me. And what you should see at this point in time is you know, what we're always used to, the typical imports. We need to create some classical registers over here. Let's see. So let's do this. We need a couple of input registers and an output register. And also let's create 2 classical registers and put them in a circuit. So let me actually run these 2 things. Then we're going to use the equality function over here for, we wanted to test if 2 qubits are in an equal superposition. So as it turns out, we can use the equality function if we properly condition them inside of a phase shift. And that's the crux when I was asking earlier, can we use the equality function? Well, the answer should have been probably that depends. We have to use it properly over here. And so if we use the equality function as our u of f, that we don't know what it is really, we act like we don't know. Of course, I have to encode it somehow here. Then what you want to do is you need to create first of all, put the output register into a 1 state. So we can do that by just using the X gate on the output register. Then putting all registers into a superposition, both input registers and the output register. And let's say we then use the function UF and apply it to our circuit over here. So UF was our equal function. Then what do we expect to see? Well, we should see if the 2 inputs are, so if we're testing if the 2 inputs are equal, and we want to see what happens in this case, we would simply have to measure, which we already do below. Let's see, backend execute. Right. What did I execute the equal to? I think I did. So let's see. If we draw the circuit, do we see the whole circuit? Yes. So we have the H's on all the 3 qubits, the X that was applied up front, and then inside we have the equality circuit. But what's missing is a measure, right? Right. We need a measure over here as well. So let me add a measure to this. Actually, I can do this. Well, let me rerun this. It's probably easier. And then we are now seeing 2 qubits that are being measured. Let's see. And the 2 qubits that are measured, oh, because I haven't printed it yet, should be the 0 and 1 qubits. And if we actually run this, well, what do we expect as an output? When we look at it, we get with an equal probability 0, 0, 0, 1, 1, 0, 1, 1. Why is that? Well, maybe it comes as a surprise to you, but this is the correct output. And the problem is, with this output over here, we cannot see the phase shift. The measurement actually is not showing the phase shift, because when you take a negative square number and a negative number and square it, our result becomes positive. So something in here is negative. We wanted to see a negative on the two inputs that were equal. That would have been the first and the last bar, but we don't see it. So there are two ways to go about this. We can now use, and this is why I like this little notebook, we can say, let's look at the state vector simulator. It's a different backend. And the state vector simulator does not actually collapse on measurement, but gives us the complete state back with including any angles. So the phase shift will become visible with a sign. But in order to do that, the IBM Qiskit API requires that we don't have a measurement in our program. So I have to go back up. I have to comment out the measurement. And I have to make sure that when I run, I'll show you the following. I have to run from the top, print this diagram. You see the circuit now doesn't have any measurement. I must not execute this simulate and show results because it's using the simulator, the Q as a simulator. I want the state vector, so I skip over it, go down here, execute this one. And now I have to closely look at the output and try to interpret the output. So what do we have here? Well, first of all, since we're not measuring, we're actually looking at 8 different states. And the 8 different states are what? Well, the output bits show as the most significant bit in the state. So the output bit would be 0 in this one. And then you have the input state. So this value corresponds to the state is 0, 0, 0, where the first 0 is from the output. The next one is 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. Okay, so now you get the idea. And what we're interested in is we're interested in the states that have, so the first states should have an amplitude of 0. Let's actually see if that's the case. So we have to interpret these in terms of the values. Oh, wait a second. I think it would be easier if we choose the other. This is always the problem. There's 2 different simulators over here. I didn't switch back to, no, this is already the basic air. This is using basic air. Let's see. Basic air backend. Yeah, I'm surprised. So let's see. We have the minus 17 over here. Okay, there's a minus 33. These are the low ones. I think this is also not correct in terms of what we're actually seeing. Let me see. Let me see what we see if we just use air on that one. I may have to actually round this. This is always difficult to work with a simulator because the output is a matter of correct interpretation over here. So this one, let's see, shows us equal values. So that's must have put in the noise. So basic was the correct one to go for. Let's see if made another mistake here. I'm not sure what's going on. Oh, I see. That may have. Do I have it? Oh, I forgot to. That's probably where it's coming from. I forgot to put the header mark on the output. I bet you that's what the problem is. Let's see. So now we have a header mark in the end, which I want to look at the state simulator. Ah, that is better. Now tells us that the first 4 values where the output is 0 have a 0 probability, and the other ones have equal probability, but we see that there is a minus in 2 cases. The last case is the 111 case, and the first case is the 101 case, where the 2 qubits are equal. And this is exactly what we wanted. So let me go back and actually demonstrate again. If I put the measure in here, and I run this circuit through the QASM simulator, you do not see the minus, but as we saw before, the minus does show up in the state vector. So one question you may ask now is there a way that I can visualize what I'm really interested in, which is the fact that there's this phase shift, this negative phase shift? And of course, the answer is you can do that. What you need to do is you need to actually apply, and let's see if I can do this correctly, a rotation so that the phase becomes visible, and that becomes visible if we rotate over the z-axis for the output. So then I could run my modified circuit with a z, and let's see, where am I? Why did this? Wait, did this run? I did. Okay. Oh, I'm measuring the 2 inputs. I would have to now measure the output. Let's see. Together with these, right? So that's problematic. Or, well, let me just give it 1 second over here. So if we no. All right. Is this? Oh, where is the? Now this doesn't seem right. I think I need to review the rotation on that one. But you can definitely see in the state vector the result that you're actually interested in. Let me see if I have a final one on this one. So there should be a, where's the phase one? This was, let's see, no. Let's see. It's hard to go through all these examples and actually find what we're interested in over here. Yeah, so here we have a phase shift example that uses an equal circuit, and in this case will tell us with the final qubit that will measure what's actually going on. But let me, in the interest of time, actually proceed with the slides at this point. There are still a couple of interesting algorithms that are following, which I want to actually have a chance to show you, because that will get us to first Grover's algorithm, and then give you a little bit of an idea for Shor's algorithm. So the next thing that we want to do is, get to another algorithm that's called Deutsch-Joscha. Before we get there, though, we need to establish a little bit of information that we use in that context. So most of you are probably familiar with the Hamming distance between two bit strings, and we're talking classical strings over here. And that's the number of bits in which these two strings x and y differ. And it's also referred, so if you count the number of bits, that's referred to as the Hamming weight. The Hamming weight is the number of bits in a string that are 1. And for when you have two strings x and y, we're going to introduce a dot operator that actually counts the number of common bits, number of common 1 bits in particular. So when reasoning about Hamming distances, there are some interesting known facts. So for example, if we count the number of ones that x and y have in common, that's the same as the Hamming weight, the Hamming distance for x and y, bitwise. And more so, if we perform a dot operator on the identity of a bit string, so the dot operator given us here the number of common bits, then if we do this over all possible values of x, so there are 2 to the n different possibilities, and sum them up, then that sum is 0 because they essentially eliminate each other. Finally, if we look at the possible values of x and then combine them with an arbitrary y, sum them up for the -1 x dot y, -1 to the x dot y. If y is 0, then what we're essentially doing is we're going to end up with 2 to the n, because all these values are going to be 1, and we're just going to sum them up. But if y is not 0, if it's not equal to 0, then that sum is going to be 0. So again, I encourage you to actually sit down and look at this a little bit more when you have time, but these are fairly trivial, if you work it out, fairly trivial examples. We need this in the following, as you will see, in combination with the Walsh-Hadamard. So the Walsh-Hadamard, as you might recall, was defined as performing a Hadamard on all qubits, and then we have an extra qubit that initially is 0. And what this does is gives us a state that is defined by the sum of the respective the states, all possible states that we have, multiplied with 1 over square root 2 to the n. So notice that this n is actually sometimes used as a shortcut notation for 2 to the n. So more abstractly, if I apply Walsh-Hadamard to a vector 0, sorry, a vector r, what this means is I have r different qubits, and apply a Hadamard to them. Then I can rewrite this as basically zeros and ones in combination with a sign. So I don't know if it's a plus or minus, because I'm putting them into a superposition. The plus or minus is determined by the r of I. Okay? So we have different vectors over here. And we can, by linearity, then use, in this case, the product of the different components of these R and S vectors, and where S is the different, the different possible states. So for the corresponding states, it's really the R that decides together with the S if we get a sign over here or if we don't. Which I can rewrite. I'm just bringing together these different terms over here into a single term. That's -1 to the S dot R, where the dot operator is still the operator that you saw on the previous slide over here, this dot operator for the common ones. All right, and this is for the state S now. So that's the resulting state that we want. So given that, we can now use these in Deutsch-Josha's algorithm. And the algorithm is solving the following problem. You have an n-bit Boolean function, so mapping n bits to 1. And this function is either constant or balanced. And I don't know which one it is. Could be constant, could be balanced. And that's what we want to find out. What does it mean to be balanced? Well, it means that an equal number of input values return 0 and 1 as output. So we can think about that later, which value is balanced and which function is constant. I mean, constant is pretty clear, and balanced, you just need to come up with an equal number of zeros and ones. So in order to determine if my UF over here is balanced or constant, the idea will be to actually use the phase shift algorithm with an angle of pi to put a sign, negate elements where f of x is equal to 1. So that basically means, well, depending on our definition over here, we want to see if something is balanced or not. Then after the phase shift has been applied, we perform a Walsh-Hadamard. And then if we have a constant f, we should see all zeros in the output. But if we had a balanced f, there should be a non-zero or maybe multiple non-zeros. And we get an output that gives us one such state with a probability of 1. So again, we are taking a function UF, treating it as a black box, and instead of trying all different values for f, x equals 0, x equals 1, whatever, and in this case, it's not just 2 values, but it's n bits. So it's a generalization of the earlier Deutsch algorithm. We want to determine if, in a single quantum run, if this function is balanced or constant. If I did this classically, I would need 2 to the n minus 1 plus 1 calls. So it's an exponential number of calls. And this is really where it gets interesting. In quantum, I have a different way of doing this. So what do? I first create my superposition, as I always do when I want to abstractly evaluate a function. Then apply the phase shift, and this will put the sign on terms where f of x equals 1. So in other words, I have, again, my f, and depending on the value of I and the vector I itself, I get a mix of signs or not signs. And once I apply the Welsh-Hadamard to this, I get a different state. So let's say state phi over here. In this case, we now have the additional 1 over n different i's. And in addition to that, the j's that correspond to the evaluation of the function f of I, and that's our j that we get, dot I. So this is going back to the Hamming distance, and we're actually counting the number of ones that I and j have in common over here, in order to determine where we need to put the phase shift in and where we don't need one. Okay? So taking this term that we saw before, what happens next? Well, if we look at the term minus 1 to the f of I and consider f, if f is constant, then really my f of i's are all the same. And they're the same as f of 0, in fact. So it is sufficient to only reason about minus 1 to the f of 0. So that's a single global phase. And the state that I get is phi. State phi is simply a 0. Now this is actually shown in detail below. So what we see below is instead of looking at the j, it is sufficient to just look at consider what j in this case actually is. So it turns out that the j cancels out, and we are left with just the f of 0 over here due to this argument that I made, so that we end up with and this is because we have a constant function over here. We end up with the 0 state for j. It's the only one that we're interested in. And depending on what f of 0 is, we may get minus 1 as a sign up there or not. And this is because we earlier established that if j is not equal to 0, then all of these terms are actually equal to 0. So I get rid of these terms, and I'm interested in only the one case where j is 0. So where did this come from? Let's go back. That's right here. If y was 0, then we end up with 2 to the n. Otherwise, the term is 0. So the otherwise is what cancels out all these other terms over here. And we are just interested in the one case where j is 0. All right, so that gives us one result for the constant case. We now need to look at the same term for the balanced case and consider what happens over here. So in the balanced case, we have an equal number of outputs that are zeros and ones, or that are actually a member in X0, if we call X0 the output set. And then in this particular case, the balancing is actually eliminating these terms so that when combined, you end up with a 0 over here. So the overall amplitude is 0. And when you actually measure, you get a non-zero j, because there will be some terms left over here with a probability of 1. I can't tell you which j you're going to get, but you're going to get some j that is non-zero. So that's the interesting part over here. So in other words, we can now use this idea actually to demonstrate the Deutsch-Joscher algorithm with a phase shift if we want to. I'm going to try this in the following. I'm going to give you another example over here. Let me see where I have this one. I think for this one, I will just, is this the solution? Maybe I should just show you the solution for this one in the interest of time. Yeah, I will do that. So I've prepared the Deutsch-Joscher example over here, which sets up a similar example that we had before. I have two different functions, an equal function that is balanced. That's actually what we used before, so we can reuse that over here. And then a constant function, which just produces the identity. And depending on what I want to run, let's put in the constant function first. I want to run a circuit that first will provide the input and the output in a header mark, but before I need to actually perform a phase shift to the output, then I have my UF function, in this case a constant function, perform a header mark on the output again, have a barrier. The barrier is just to separate our UF from the final output, where I have to prepare Q in with another header mark, then measure. So we do this. What's going on? Oh, it doesn't like identity anymore. Okay, that's just a warning. Interesting. And this is the circuit that we get out of this. So the identity function is the function that we're actually interested in right now. And what do I get out? I get out 0, 0. So this is actually telling me that I have a constant function in this particular case. Let me repeat the same example. So for a constant function, I should get a 0, 0 with a probability of 1. But if I use a balanced function equal to and run the same program, what should I get? Well, you will see. In this case, I get a 1, 1 with a probability of 1. Again, this is, of course, on the QASM simulator, but it shows you the principle that we're using in the following. So let's go back to the slides. And first of all, I want to summarize. We know that, or it is known that an efficient reversible classical circuit can be implemented for any quantum circuit. So in particular, we can use this for the construction of an inverse function and also to unentangle. We have to use some non-classical operation with Hadamard's and entanglement in order to get a quantum advantage. For example, to use the techniques for phase shifting. And then the big question is, are these algorithms by themselves already sufficient? So let me see. To get a little bit of an idea of what we can now do with the building blocks that we have learned about, particularly the phase shift, the Deutsch-Jorscher algorithm, and how they can be combined, let's consider a high-level explanation of Grover's algorithm. For a given input x, Grover's algorithm is trying to actually perform a search. So f of x will be 1 for one of the elements out of 2 to the n possible inputs. I don't know which one. So think of it as being a 3-qubit or 3-bit question, which has 2 to the 3 or 8 different possible outputs. Then I don't really know which of these boxes contains a prize. Maybe it's this box over here, the third box. What we have to do classically is go through all the n boxes in the worst case, whereas in quantum, you can solve this problem in square root n steps. So how can this actually be done? The key to it is to perform 2 transformations. There's actually 2 operators over here. The first one is the phase change operator that you've already seen. And the intuition of this one is as follows. So with the phase change operator, if we have a function that actually checks for membership, we can then use the phase change after, of course, as always, using the Walsh-Hadamard to prepare everything in a superposition, such that the phase actually changes for a known input. You can see that the phase over here for one of the boxes has been inverted. So this is the algorithm that we already learned about. In addition, there is a diffusion operator that is applied next. So you first have the phase change, then the diffusion. The diffusion operator performs a Welsh-Hadamard, which is this first step over here. And oops, this step. And the Welsh-Hadamard essentially results in a phase shift that changes the sign and equalizes the amplitudes over all these amplitudes over here. So what this does is it will actually look at the relative amplitude of these different boxes. So that amplitude is indicated by the line that runs through over here. That's the average amplitude over all the boxes. It's lower than these 7 boxes because the one box actually has been phase shifted, so it's negative. If we now average and reflect over the average across that line, that will reduce the amplitude of the first box by exactly this amount and bring this box down here. And take this box and reflect it to the top so it ends up here, which essentially gives us this picture down here. So all these 7 boxes have become lower, whereas the diffusion actually reflected the negative phase to become now the dominant one. Now, the claim of this one is, Grover's algorithm, that you can actually repeat this process. So you repeat this process square root n times on average, and then you measure. And this will result in more amplification and all of these guys coming further down each time. And you just have to know how often you have to repeat it. And that's the square root of n. There's some math behind that, why it's square root of n. That with a high probability, you can then measure and identify the box that you were actually searching for as a correct output. And that brings down the complexity by a significant amount for large n, which is one example of a quantum advantage that you can glean out of this. All right. So finally, I want to look at Shor's factoring, because that's one of the always cited algorithms for having the most potential in quantum. And for Shor's algorithm, what you end up with is an interesting observation. So he actually, my guess is he was closely following what had happened in building blocks for algorithms, and his knowledge of some of the factoring, also in terms of the classical results, allowed him then to combine different algorithms in a quite interesting way that we hadn't seen before. So think about public key encryption, where you need a large n that is actually the product of 2 primes p and q. We use that to encrypt messages and then decrypt them. And we need relatively large p's and q's so that it becomes computationally infeasible to reverse engineer n by brute force, just trying out all the different values. Classically, we can certainly say that that's a safe method as long as your p and q are large enough. In other words, if your key length is long enough within an RSA key. So in quantum, though, Shor discovered an algorithm that allows you to very efficiently find the p's and q's that actually factor the n. And it's based on an interesting observation. For some number of a that's not divisible by p and q, the following sequence repeats itself with a period of r. You have an a1 modulo n, a2 modulo n, a3 modulo n, up to n, and then it repeats itself. In addition, r, the period over here, in other words, the length of the sequence, always divides p minus 1 times q minus 1. So if you can discover r, you can then actually find p and q. That's the key. So let's look at an example. So the example is, let's assume our big number, not so big, is 15. And we know, of course, that the prime factors are 3 and 5. And what we want to come up is actually an A. So let's try for an A. So where does the A actually come in? The A is some number that is not divisible by P and Q. So A, we choose a 2, start with a small number, is not divisible by 3 or 5. And then we take, as you can see here, A1, A to the 2, A to the 3, A to the 4, always modulo n. We know n, of course. So it's 2, 4, 8, 16 modulo 5 gives us 1. And you can keep computing. What happens next is actually 32 modulo n is 2, and so on. You see that the modulo 2, 4, 8, 1 actually repeats. So you get this pattern with a repetition length of 4. That's our r. And 4 actually divides 3 minus 1 times 5 minus 1. So that's, let's see, 2 times 4, which equals 8. So if we find r, then we just have to try different values with a +1, -1. And that way we can determine P and Q. And the problem is actually R. R is difficult to find for classical computers. It has exponential complexity. On a quantum system, however, it is in the order of quadratic with a bunch of log n's. So that's actually not high overhead. And how does this actually work? So for this one, I'm just going to give you a really high-level description. First of all, it's an interaction between quantum and classical, which many interesting quantum algorithms are. The classical part is you start out with n, and then choose an a that is less than a, and you can start with 2 as you wanted to, and see if the GCD between a and n is 1, meaning it's not divisible. If it isn't, then then a and n over 2 are factors of n. We're actually not interested in that. So if it is, then we are going to try to find the period by using a quantum algorithm. And the quantum algorithm will encode, in this case, our input over here, which is our n, together with a set of functions that are actually performing a conditional rotation on a set of n qubits that are initialized with 1, and give you a phase kickback to the respective upper qubits, followed by a QFT to filter out the result, which then, when we decode what comes out of here, gives us an R, which we check. If R is odd, then we actually go back and choose a different A, because what we want to do is we want to add 1 and subtract 1, remember, to actually come up with a possible result. There's actually a second check over here where we check if A to the R over 2 is -1 modulo n. If that's the case, again, choose a different A. Otherwise, we have found factors that you can now determine by A of to the R over 2 plus 1 or -1, and the GCD of that one with n. So that's the crux of it. And as you can see, the computation in the classical part is fairly simple. It's the green part actually that gives you the quantum advantage in this particular case. All right, so I think I'm going to stop at this point in time. There are some additional slides in the deck that you can actually take a look at if you want to. I will stop with the gate-based programming and try to switch to a different one, a different paradigm, because I haven't had time to actually cover that. And I may only be able to cover part of that. So if we actually look back at where we're standing in terms of the overall, I think I have that at the end over here, wasn't it? Oh, well, we can go to this slide. I have covered everything, including the IBM Q and some additional algorithms. I want to now give you an idea about quantum annealing before we break. As you can see, we're running a little bit behind because I went into more detail. I think it was necessary to actually explain some of the intricacies, particularly with the gate-based programming. But I will give the quantum annealing at least half an hour that you get an idea of it before we finish around 4 o'clock. All right, so let me see if that's actually something that we can still do. There should be enough time for that. Let me quickly switch over to the other algorithms. So quantum annealing is a different approach to quantum computing, and as I explained earlier, it's also got a different objective. If we look at, for example, the capabilities of quantum annealing, it's not for general purpose computing, but rather for optimization problems. So it is actually related to adiabatic quantum computing. When we look at an example for annealing, you can think of annealing as the ability to find a local minimum in an energy landscape, which with normal simulated annealing, let's say we have a ball that we let bounce onto a surface, and it will end up potentially in the local minimum. With quantum annealing, even if you end up in a local minimum, you can exploit the capability of quantum tunneling to dive through energy barriers and are more likely to get to a local minimum this way if it's one that's nearby. And quantum annealing, actually, you start in superpositions, so that's something it has in common with gate-based programming. But this is really to be then driving from a superposition state into a minimum energy state. That's the idea over here. So with quantum annealing, the annealing process is raised through energy barrier. In this case, you have two energy levels. The qubit can be 0 or 1, and thereby also two minima that you're actually interested in over here. So with a so-called annealing bias, you can influence how these two energy levels relate to one another. So for example, I can give the state 1 a higher probability by being lower in energy over here. In addition to that, you have the notion of qubits. So that's what you saw in the previous slides, the state of qubits and how you can bias them. And then couplers. So couplers are actually giving you a connection between two qubits to influence the energy exchange between them and generate a landscape. So this is the energy landscape that you see. In an ideal world, your annealer should drive down to a lowest energy state. This would be your answer. And that's exactly what's called the adiabatic evolution of state. You start in some known minimum over here on the right side, and then change the energy landscape in terms of bias and coupling, and end up by slowly evolving the system so that you can tunnel between adjacent low energy states and hopefully end up in the minimum or a relatively low minimal state. Now the interesting part is this goes back exactly to where we started out. We actually have the ability also in gate-based programming to express problems in terms of a Hamiltonian. And a Hamiltonian is essentially a function that maps eigenstates to energy. In fact, problems that we're describing here can also be evaluated in a gate-based program, but not to the efficiency that adiabatic hardware that currently exists currently allows. So the adiabatic hardware in that case is constraining you to certain problems, but allowing you to run rather large problems. How so? Well, there's several parts of the Hamiltonian that are of interest over here. So there is a initial part. That's the part that is used for the tunneling and affects with a global value each of these qubits over here. And then, but that's on an X rotation, as you can see. So the X over here is actually indicating the degree of freedom. They also have a Z rotation. And for these qubits, there are then two parts that you can actually control in the program. The bias and the coupling. So the bias is a factor for the qubit value, which can be +1 or -1, let's say. And the coupler is essentially telling you what the energy exchange between adjacent qubits can be. And over time, the Hamiltonian evolves by an increase to the decrease essentially of A of S, so A of S goes down quicker and quicker to 0, and an increase in the B of S, which is the other term that brings in more of your optimization constraints to the problem. And you can see on the right side how over time the AS actually goes down and the BS goes up. So in adiabatic quantum, then you have a more general formulation. So this is adiabatic quantum computing as opposed to adiabatic quantum annealing. And the difference is essentially that you have a full freedom on the Z terms with the bias and couplings on the Z rotations as well as the X rotations. The interesting part here is if you had this full freedom on the Z side, which the D-Wave annealer or quantum annealing in general do not, then you would be equivalent to gate-based programming. And so nobody has implemented such an adiabatic quantum computer yet. So what we are left with is two local Ising expressions with essentially these spin up, spin down states for the qubits, the S of i's or S of j's over here, that allow us to express an optimization problem as a quadratic unconstrained binary optimization problem, where we are trying to actually minimize a function for given biases Q, I, J, and sorry, this should be, this should should be a B or something like a bias I, and then coupling Qij between two qubits. And you can rewrite this also in terms of a 0-1 state. And that's what we're going to do in the following. For qubit I with a bias A of I and a coupling B of ij between two qubits. So what we're doing is we're basically juggling different energy levels of these qubits indicated by weights and couplers between them so that they can exchange energy over time in multiple iterations, which the machine does for us. Okay, so then the problem basically comes down to how can I formulate problems? And essentially I can view a quadratic problem as a graph with nodes and edges. So this is my weight over here for qubit 0. And this is my weight for qubit 1. And then I have a coupling between the two qubits. And when I formulate a problem, then a problem is basically an expression of my problem from an Ising model transformed into a QUBO quadratic binary optimization, so that the program is basically defining my biases and couplings, and the outcome will be a vector of qubit values, so all these q zeros to qn-1 that minimize the objective function subject to the annealing process. And this has been implemented by D-Wave for up to 2,000 qubits and 6,000 couplers, using essentially the same technology that is being used for superconducting silicon. So the IBM transmons are also using Josephson junctions, but they're using them in a different way in the D-Wave. And for the biases, we can have values between -1, +1 for the couplers between -2 and +2. And not all qubits are connected to each other, of course. We'll see later on in a graph how they're actually being combined. Actually, here is such a graph. So you have local qubits in an RF squid that's equivalent to a transmon, which implements 8 different qubits. And each qubit on the left side is connected to 4 qubits on the right side, which creates a 4-4 click bipartite graph. This one is embedded in a chimera graph. So the unit cell that you saw in the previous slide is in the red box. In addition to the 4 connections inside the box, you now have 1 additional connection outside the box. So for the left qubits, that's actually going down. And for the right qubits, it's going over horizontally. So you have a vertical and a horizontal connection to then have limited connectivity between these so-called unit cells. This will later on actually in the next generation change to a Pegasus graph that I'm going to jump over. And in the interest of time, I'll just going to mention that, of course, you have errors over here as well. Again, these machines are superconducting, so they have to be cooled to nearly absolute 0. And you get noise in here. So you run multiple shots, just like we did in the IBM case. And essentially, the runtime is dominated by the setup of the problem with the biases and the coupling values and the readouts, but not so much actually running. So you can run many shots, many repeated experiments. So how do you actually program with this? And usually I would run some exercises. I don't have the time to do this. You can actually use the resources that are on the web page to go through some of these exercises. Again, they are Jupyter notebooks and also a D-Wave Ocean Python class that you can use in order to program the machine. The programming itself is essentially a combination of using weights and couplings, weights and coupling strength. So let's look at the weights first. So that's this term over here in blue. If a qubit can be in a 0 or in a 1 state, what happens in terms of the A? If the factor A is negative, then what happens is you will derive, when the qubit is 1, the overall energy down, because it's multiplied by the -5. So that's basically giving it a bias to say, I want this qubit to be 1 in order to reduce my energy, because in the end, an annealer will seek to find a low energy value. If it's 0, then you have an equal likelihood for the same energy, no matter if it's 0 or 1. So basically, you're saying, I don't care what the value of this qubit is. But it's positive. It's the opposite. It's saying, I want this qubit to be 0. I want to drive this qubit towards 0 so that the energy is low. And if you think of it like that, then the question is, where do the couplings come in? So the couplings will now combine 2 qubits and create a strength between them that could be stronger or less. So let's see what happens with a -5 for the coupling or strength values. With a negative strength, you're basically saying, I want both qubits to be true, to be in the 1 state, and that will drive energy down. If the strength is 0, no surprise here. I basically don't care. And if the strength is positive, I want neither qubit to be true. So you're trying to drive a state that's opposite of the last one, where both of them are true. It's not clear which one you're following. You're allowing any of these three states to be reached in a final minimal energy value. So this was looking at pairs of qubits. And usually I would now actually go into a quantum apprentice. It's a little spreadsheet that is on the web page. You can pull that down if you want to and look at it. And it gives you the ability to implement simple programs and evaluate them. So the idea is you have a Hamiltonian that's expressed by a bias, another bias for 2 qubits, and a coupling between these 2 qubits, which is essentially the picture that you see over here. You can use a dial to change the bias of the first qubit or the second qubit, and you have a third dial that actually defines the strength. And now you can put in different values. This is what you program. You actually change the value over here for the A's and the B's. And this will allow you to then automatically look at a energy table that as an objective function depicts the resulting energy value. So in this case, we have chosen biases or weights of -1 and 0 and a strength of -1. And what we're seeing is that this implements some function that in case of the qubit values 1 and 1 reaches a minimal energy state signified by the dark blue in the objective field. So this is what we're driving this into. And it's essentially both qubits are 1. So you can actually come up with simple 2 qubit relations by programming weights and strength in such a way that you implement equality, not equality, or implies. And since we don't have the time, I'm not going to go through the spreadsheet and actually do this. Usually I would. You would then see that in order to come up with, for example, an equality, what I want to do in this case is I want to choose a weight of 1 for both qubits and a strength of -2. So what does this do? Remember that we have our A1 Q1 plus A2 Q2 plus B1 2 Q1 Q2, which will give us the objective value, for example, this one over here shown. So you can actually do the calculation yourself. Clearly, if Q0 and Q1 are 0, you're going to get a 0 over here. If one of them is 1, then the strength doesn't matter, the B doesn't matter. You just end up with a 1. If both of them are 1, then you get a 1 plus 1 minus 2 is 0. So this drives you into a state that is lowest energy when both qubits have equal value. Hence, it's an equality that you're expressing with the Hamiltonian through the specification of weights and strength. So you can try this for not equal, for imply, and many other cases, and then actually go to the Ocean, D-Wave Ocean program, which in a simulator you can first run with an exact solver, and later on you can run on a real machine that would, for example, in this case, look at a program to implement equality by simply specifying the weight of qubit 1 and qubit 2 and the strength between qubit 1 and qubit 2. So that's your QUBO or your Hamiltonian that is derived from this query. If you want to think of it as a query, it's a QUBO specification, such that you then print out the different values in terms of the energy that result from the qubits. And that's shown over here in the output. So we are after these two values where the qubits are actually equal, as you can see. Those are the minimal energy values. And that's an output that you would see when you run this Python program or a Jupyter notebook that's equivalent to that. You can throw that on the D-Wave hardware by first signing up. Similar to the IBM Q experience, they have something called D-Wave Leap. You sign up for the platform, get a token, save the token in your account, and after that, you can use an embedded composite of the D-Wave sampler and specify the number of shots, repetitions of samples that you want to get, and then summarize the output that you get essentially from a dictionary using just simple Python. And this would indicate in this case that all but one solution were found to be exactly this equal state 0011. There's one shot that actually was recorded for a non-equal case. So you see that the hardware does bring in errors as well, just like we saw on the other side. So we can then make this more complex. So for example, here we have an objective that you could actually try out for yourself to create that implements logical OR, where the resulting value is the third qubit. And the challenge here is to find A's and B's that give you a solution to this OR. There is a solution to it. If you want to try it yourself, try it first in the quantumic, what is it called, the spreadsheet, and then maybe look at the result and see if it's correct, or even try it out yourself. I have some additional slides that will actually go into a little bit more detail in terms of embedding QUBOs that require a complete graph with 3 qubits in the unit graph that you see on the right side. And due to time constraints, I will quickly walk through this and just basically tell you the idea that what we can do is we can actually use neighboring qubits to create copies. And this is completely different from gate-based programming, where you have the no cloning. A copy is really just a logical copy. What we're doing is we are mapping our logical qubits onto physical ones. So this one goes here, this one goes here, and that one goes to first qubit 0. And what I now want to do is I want to bias qubit 4 to be equal to qubit 0. So I can actually not really copy, but bias my other qubit to change its energy to equalize with Q0. And I do so by using, well, what? The equal relation that we actually saw before, with the following weights and strength, more or less. But I have to be a little bit more careful because due to the chaining and so on, I have to adjust them. There's an algorithm that actually goes through that to further adjust that by splitting the original weight. So when you saw the original weight is split into 0.5, and then add it to the ones over here. Again, I'm gonna gloss over this, and in hopefully the final minutes, if the recording doesn't stop, give you a little bit of a taste of how you go from a program that, for example, in this case, gives you a Boolean OR with an embedded problem where you put the task of embedding your QUBO with different weights and strength to the D-Wave compiling framework and decouple it to make it manual. Manual in the sense of placing your qubits that are logical qubits on physical qubits. So physical really means that if we think of the unit graph has some kind of numbering where this is qubit 0, this is qubit, and I have to think about this, 1, 2, 3. They're actually in this order. And then that's one unit graph. The next unit graph would continue on the right side, and then eventually, once you've filled all these rows, it goes to the second row over here. So by doing that, the QUBO that you express is now actually tied to a physical qubit. And this can be useful because sometimes the auto embedder, the minor embedder that D-Wave uses will not find the most efficient embedding. And you can actually be more explicit in this as well. So what I did over here is I said actually qubit 3 should be split over 0 and 4. So I would use this and that qubit, physical qubit, to create a virtual qubit on top of it. And this would be my Q3. Instead of that, I could have actually said I want a Q3 and a QQ3 that I then connect with these weights and some strength to create an equality and make sure that they are the same qubits. So there are different ways of actually driving the embedding. That's all I want to point out at this point. I'm going to skip over these examples and just point out that there are some neat examples for building a half adder, first of all, then showing how a half adder can be efficiently embedded, how a half adder can be extended into a multi-bit adder, and how you deal with problems as you are embedding multiple qubits across different unit graphs into, one virtual qubit into multiple physical qubits. There is an interesting example that if you have time, you may want to look at the social network analysis, which gives you at a very high level an idea of the practical capabilities in terms of graph problems that can be solved on the D-Wave. But for today, I think I'm going to run out of time, so I won't be able to give that one any justice. All right. I apologize for rushing through this last part, but overall, I think I want to summarize by saying you have seen two different paradigms of quantum computing with some practical examples and programming examples, at least on screen also for the second one. Of those two, the gate programming that we went through in more detail has the potential to give you a quantum advantage, by definition being more performant in terms of a large constant factor, if not a quantum supremacy, in the sense that it breaks complexity classes as demonstrated with Shor's algorithm. Meanwhile, there are new algorithms coming out, such as VQE and QAOA, which combine gate-based kernels with regular classical computing. And that may in fact be also where some of the future interesting problems are coming from. And in the future, we may see more of that. What remains to be said about the quantum annealing approach for the D-Wave is, while the gate approach is up to 50 qubits, quantum annealing scales up to 2000 qubits. However, it is constrained in its applicability to problems that are coming out of the optimization foundation. So if you have a problem that's already an optimization problem and you want to try it out, you should definitely look at the annealing machine as a viable solution. For many other problems, especially these problems breaking complexity classes, looking at evaluating the state of functions abstractly, that's when you want to look at the gate-based programming. I hope this gives you a little bit of a taste of quantum programming. I encourage you to also go back and look at our resources. So there were multiple resources. If you take a look at the web page over here, and among these resources are pointers, of course, for additional reading, programming exercises that you may want to take a look at. And on the original homepage at the bottom, a bunch of additional resources in terms of reading resources, in terms of a class that we've been teaching for multiple rounds now at NC State, as well as boot camps for programming with interesting results and algorithms to look at. So I hope I've given you a taste of quantum programming, and I hope that maybe you will dive a little bit more into it, let it be by taking additional classes online or physical whenever we have a chance for that again. And I will thank you for your time. Bye.